Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Ladies and gentlemen, welcome back to another video or to another live stream. And please make sure to join the server. You're gonna find the link in the description so you could get notified of next live streams. You can also vote for the next live streams. Okay, so let me share the live stream real quick. Announcements. What? There you go. And Zig stream. And hello. Well, there's no name. Hello there. How is it going? Let's see. The microphone is fine, camera fine, cool. Okay, just gotta wait a bit for interested people to join in, and we're going to start the journey. Alright. Good, just started learning Zig and found your videos, really awesome work, and today I finally made it to the live stream. Amazing. Amazing, thanks. Today I finally made it to the live stream. Nice. And welcome. Alright, just gotta wait a bit more for interested people to join in, and we're going to start, or should I say to continue. Alright. Three minutes in. Great. All right, amazing. 20 hours ago, stream 2. 20 hours ago. Cool. 20 hours ago. That was 2 days ago. Alright, so cool. 2 days ago. 2 days ago, first stream. Nice. At some point you gotta actually split this into multiple units, to multiple files, but I think for now it's fine. Alright, so how much time have... Alright, 4 minutes and a half in. Gotta wait just a bit more and we're going to start. Cool. Is there any questions, by the way, while we're waiting? If you guys have any questions, let me know. Right, so I think we're going to start. Okay, let's go. So yesterday in previous stream, we indeed got a black window in, but the last part was kind of rushed. Welcome to supporter. Oh, amazing, thanks. The first supporter member, interesting. I didn't even think that was still up. Thanks, thank you so much. That's interesting. First member to join in. I'd have to revisit the the features I've set it there and see if I guess I'm not sure about the features of members of supporters yet. I forgot, but I'll see after the stream. Okay. Anyway, so let's get going. Let's continue. All right. So as I said yesterday in previous live stream, we got a black window in. It was working kind of fine, I guess. There was some errors because I just forgot some things, and you know, just like it was the call of the prayer, so that was my and I just ended the live stream. But yeah, so right now I just kind of reverted back to the previous Git, like the previous code that we have committed to Git, and so we just continue. It wasn't really that much, and it was kind of rushed, so let's go. All right, so what we have. So let's see. Now let's actually deal with the rendering, the frame by frame stuff. So we're gonna say while, let's see, while, actually not while, if swap chain, if maybe swap chain, let's see, where is maybe swap chain? It's right there. Why it's not? Well, anyways, maybe swap chain. Let's go. And there you go. So now let's just have a look. CD log. Oops. Well, c.sdl log. Let's just say is hello world, just so I know this actually works. And let's see. Zika build run. Alright, as you can see, every frame right now we're getting hello world. Cool. So there is a swap chain. Lovely. So now what we gotta do, let's see. Where to start? I need some time to start my brain. Okay, hold on. Alright, so we need a semaphore and we also need a fence. So let's get actually that going. We've done this before, but right now we're gonna do it right. Where is the dispatch? The instance? No, the device dispatch equal to struct. Let's go. So we need to load some function pointers in. We need create fence. Okay, cd.meta.child c.pfn vk, let's see, create fence equal to undefined, and then we have destroy fence, cd.meta.child c.pfn vk destroy fence. We also need to be able to actually create semaphores and destroy them. So I'm just gonna copy that guy, and instead of fence we're gonna have semaphore, pretty much. Okay. Alright, nice. Now we also need to be able to wait on fences, I believe. So wait for fences. Well, let me just copy this over. Wait for fences, I believe. So vk wait for fences. Great. Undefined. Nice. So create fence, destroy fence, wait for fences, create semaphore, destroy semaphore. Nice. And what about the swap chain? Get swap chain images. Yeah, we gotta add also some stuff here. Let me just copy this line over. And let's see. So vacate, we need first of all, I believe, yeah, acquire next image, KHR. Okay. Well, in fact, acquire next image, KHR. Oops. Acquire next image. Undefined. Let's go. And next up, we need the, let's see, Q present. So vacate Q present, KHR. Q present. Let's go. Undefined. Now, what else we need? Let me try and remember. I think that's all. That's all, I guess. Acquire. Oh, I forgot one little thing, but not here. I forgot it in the fences. We need that too. So, which is reset fences. And that's the thing that I forgot to do last stream, when we were just rushing things out. I forgot about that completely, because every time you wait for fences, you have to reset them. I believe. Reset fences. There you go. And let me make sure that it is indeed loading all the function pointers correctly. Let's go. And also I'm going to always keep an eye on the release, otherwise we're going to end up with a nasty UB and we're not going to know where to even start fixing it. Okay, all good until now. Alright, very amazing, very amazing. So let's now figure out how to deal with this. Well, first of all, we got to create some fences and semaphores objects. It's gonna be quite simple, but one thing that I noticed last stream is that instead of Kimzo, welcome to the live stream, how is it going? Now I have a question for you, bro. Welcome every time. Like anytime, just ask the question, let me know. You're welcome anytime. So but I may just delay answering the question for a bit while, you know, if I was really thinking about some problem, how to fix it. But just ask the question whenever I'm free. I can basically answer it. So struct fence and oops, actually const fence equals struct. My brain is still kind of just starting up. Okay, const self equal to this. Right, and we're gonna need some handle, which is gonna be like fence, I guess, vk fence. And then we also need allocation callbacks, which is gonna be c.allocation callbacks, and it's gonna be an optional pointer. And then we're gonna have a dinit function. We're not gonna have an init function. We're basically gonna use a factory function inside of the device, which gonna create the fence. Oh, but yeah, as I said, I actually noticed something in the last live stream, which is that we do not have functions to deal with individual fences or individual semaphores. We always, in Vulkan, it seems like they always go ahead and kind of always try to deal with a collection of fences and a collection of semaphores. Okay, a question: Do computer science as a major in universe useful, or study something else and learn it alone? I think depends on yourself first, and on your goals, and also on your country. For example, in Morocco, if you want to work on like the regular jobs, you probably want to go to university either way. But if you, let's say, going to just look for a remote job, you may find something like without university. But honestly, if you really just want to work on, like, you know, the regular job, you just go to a company and work, you probably want to go to university to just at least get the paper, you know, because a lot of jobs do require the, you know, the paper. indicating your professionalism kind of thing. But it really depends on your goals, pretty much. I don't feel like someone who can give good advice on that, but it really depends on your goals and a lot of other factors. Assalamu alaikum. Wa alaikum assalam, MYD. Welcome to the live stream. Okay, so the init. Now, as I said, we probably have to, honestly, instead of dealing with one fence, we probably would like to deal with multiple fences, because all the Vulkan function I've seen that deals with fences deals with a collection of fences instead of a one. So maybe I should consider that in my design, I guess. So honestly, yeah, that's probably what I'm gonna do. Kimzo, yeah, that's sad, man. Why I need a paper to say I'm good or not? I mean, you could still just learn computer science on your own, and then, you know, make your own project, make your own kind of company even. It's like, but the thing is, without a paper, you're gonna have a bit of a rough time. And in fact, and the jobs that needs a paper, usually they need like PhDs and stuff like that. But it really depends also on the job. Like, for example, if you're gonna work, like if you're gonna program medical equipments, then surely they're not gonna take that. Just trust me, bro. It's just not gonna work like that. You need the paper to actually, like, basically the paper is just someone, like some university, kind of taking the responsibility of guaranteeing to people that you're capable of the job listed in that paper, pretty much. I'll let you complete the code so it's not QA. It's fine, just a question, and if I have time I can answer. Self-studying, but the job needs a degree. Yeah, so for me at least, I do have an online, I study online right now, although it's just the first year. And in fact, it's not that hard, you know. It's like, it's online async learning, so I have total freedom. I just study when I need to study. And in fact, I don't really learn that much. I mean, most of the stuff I already learned. But the amazing thing about university, though, is that you learn the terminology, and also you have more confidence in some of your skills. Is because of the fact that you have gone through, you know, a rigorous path of doing things, instead of just, you know, you trying to explore the field and just learning as you go, basically. So I would still recommend a university, I think, but again, as I said, it depends on your goals and who are you as a person. But anyway, the init. So yeah, as I said, Vulkan functions usually deals with a collection of fences instead of one fence. So honestly, I think I'm gonna take a little bit of a unusual design, just to not compromise performance, I think. So I'm going to go with an array list, I believe. An array list of fences. So I'm going to deal with collection of fences. So basically, I'm not trying to force my design on Vulkan API. I'm trying to shape my design depending on Vulkan API. I'm not really too much concerned about convenience, etc. So anyways, so we got an array list, but we also, since we have an array list, we gotta need an allocator for that. So an allocator, well, it's gonna be a cd-mim allocator. All right, cool. So, and by the way, there's gonna be probably some stream in the future, you know, just playing some multiplayer games. I actually understood how to make multiplayer games and how to do port forwarding. So in some future stream, we can do some gameplay in Q&A, for example, in Mindtest or OpenTTD or other open source games. But anyways, so the init void, and it needs self. Okay, great. Now in the init, you probably want to go through all the fences. So for handles, yeah, that would be cool. Nice. Yeah, I just figured out yesterday, I think, with some of my some of the people in my server, and it was pretty interesting. I figured out how to do port forwarding, and I figured out how to launch a server, and we had some fun time. It was very interesting. I'll probably make some live streams in the future about that, but just not now. I think right now on my live streams on my channel, I'm going to just focus on getting maybe a triangle or maybe even a cube, a Vulkan cube, and then we could start doing from time to time some gameplays or some other videos. Like, for example, someone have recommended to me to do a crash course on Zig. That would be coming in the future, but right now I just gotta focus on this project for a second. So anyways, for handles, for self.handles, now for each handle we're going to destroy it. We gotta need the device, so we gotta also need the device. Let's see, it's the device, there you go. Okay, cool. Now we're gonna basically say device dot dispatch, I believe. Yes, dispatch dot destroy fence handle. Now this can't fail, so yeah, that's nice. Now after destroying all the fences on the array, oh, by the way, handles is an array, so I gotta actually access the items field. There you go. Okay, great. Now after destroying all the fences in the array, I should deallocate the array. So I gotta say, let's see. Here's how you do it. Handles.dinit, I believe. Yeah, pretty much. Now self.device.dispatch. There you go. Use a declared identifier self.handles. Okay. Alright, great. Now that's the init. We also need a wait, like to wait for all the fences in there. So here's how we're gonna do that. Self void. And if you have any suggestions or something like that, let me know while I'm designing this. This is kind of a new design kind of thing, trying to fit with the Vulkan API there. But anyways, wait. So here, self.device. So APIs, for example, like WebGPU, WGPU, you know, and Dawn kind of tries to basically design their API for convenience and also to basically satisfy all kinds of APIs and be as general as possible, so they could basically and with that comes the problem that, you know, like you cannot really design your API as better as possible, and you have to do some compromises and some trade-offs. But in my case, I don't care about convenience. I don't care about any of that stuff. I have only Vulkan API, and I'd like to design my project not to fit Vulkan on my thing, but to fit my design on Vulkan. But anyways, when you do void, why you did void? When you do error void, why you did void? In the case of the init, like you can indeed go ahead with an error, but I don't need here that guy. Why? Too simply because I'm not going to be throwing any error. And in fact, you could, like in Zig, you can do whatever you want. You could even go ahead and deinitialize, or the deconstructor, you can in fact go ahead and throw an error. But as a general thumb, a rule of thumb, don't throw errors from a deinit function. Like deconstructors should never throw errors, like as a rule of thumb, and that's generally, what can I say? Basically everyone agrees on that point. But you can indeed go ahead and throw errors, but you may have some problems with defer and defer init, deinit and stuff like that. But anyways, so self.surface device.dispatch. So if there is anything that requires throwing an error in the deinit, try to basically put it in the initialize instead of the deinit, and then just store it so you could reuse it in the deinit function basically. So yeah, self.device.dispatch. Now we gotta say wait for fences. Okay, there you go. Now let me see the signatures of this guy. Okay, so here we have a device, we have that guy. Okay, let me just copy this over and let's see where we have the wait function. Okay, great. Now we have a vacate device. Now the device is basically device dot self.device.handle, and then here I have utility2, which is basically handles.len, self.handles.length, basically how much fences you have, and then the pointer to the data, to the actual handles. So handles.ptr, I believe. Actually, no, dot items. Okay, dot items, and then you could say dot ptr. Okay, great. Now vacate bool 32. Now here, do you want to, like, I think, wait for all fences, or only wait for one fence, only one of the fences? Hold on, let me just get the documentation so we can be sure of what we're doing here, and not just winging it. So let's see the registry. So as you can see, wait for one or more fences to become signaled. To wait for one or more fences to enter the signaled states on the host, call these guys. So device is the logical device, fence count, okay, all right, there you go. Wait all. Wait all is the condition that must be satisfied to successfully unblock the wait. Is the condition that must be satisfied to successfully unblock the wait. If wait all is vacate true, then the condition is that all fences in p fences are signaled. Otherwise, the condition is that at least one fence is signaled. Interesting. And there is a timeout. Timeout is a timeout period in units of nanoseconds. Oh, nanoseconds, not seconds. Timeout is adjusted to the closest value allowed by the implementation dependent timeout accuracy, which may be substantially longer than 1 nanosecond and may be longer than the requested period. Okay, if the condition is satisfied. Alright, so I'm just gonna read with my eyes, so be fast. Just kind of revising this with the condition. Oh, timeout is 0. I was actually using maximum integer. Interesting. It does not wait. Alright, well, it does not wait. It simply returns the current state of the fences. Vacate timeout will be the condition is not satisfied. In this case, the condition is satisfied. Okay, interesting. While we guarantee that vacate wait for census must return in finite time. Alright, cool. So the success codes are vacate success and vacate timeout. And on failure, this could be out of host memory, out of device memory, or device lost. Interesting. So basically, if timeout is 0, then it does not wait. It simply returns the current state of the fences, and it actually returns vacate timeout. And of course, if it's something else, so all right, gotcha, makes sense. So this just gonna be wait all. Let's see. For all. Wait for all. Okay, so for all, I guess Boolean maybe, but of course Vulkan functions doesn't take Boolean, so I gotta actually make this 1 or 0 basically. So how to do that? Well, math maybe. Let's see, bool mask, no. Maybe let's see here, bool int from Boolean. Let's go int from Boolean for all. Why did you choose Zig over Rust? Delta pi. As I said before, Rust is just not for such projects. I did try Rust before, in fact, and I did even reach a triangle, etc. But it's just so painful to work with for such low-level, inherently unsafe projects. And your code just becomes a spaghetti of unsafe code, pretty much. It's like the whole point of Rust is safe code. And the thing is, you have, like in Rust, instead of fixing undefined behavior or bugs when they come over to you, you have to constantly prove to the compiler, to the Rust borrow checker, that what you're doing is right. Right, they don't have unsafe figured out yet. No, it's not. The thing is, if you actually look into the guarantees that you have to uphold for the Rust analyzer, the Rust borrow checker for unsafe code, Rust borrow checker unsafe guarantees. Hopefully I got that right. Let's see. Understanding, bypassing. Let's see this guy. Well, anyway, it doesn't seem like there's some list right here real quick, memory safety. But basically, there is quite a lot of guarantees that you have to guarantee and uphold for the compiler in your unsafe code. Otherwise, everything can break. Like literally everything can break. Because the Rust compiler uses all of those guarantees that you have to guarantee, basically, to optimize the stuff that it does and to assume some things. And if your assumptions are wrong, then everything could happen wrong. Everything else could happen wrong. So that's basically it. So honestly, for me, and especially for such hobbyist and also inherently unsafe projects, I'd rather just fix the bugs that comes up instead of trying to constantly prove to the compiler that this thing that I'm doing is actually safe. And also there's a lot of false positives when it comes to doing that. But yeah, that's just the summary of why. But I may do a video later on this whole kind of why I chose Zig over all other languages and why Zig and not Rust, etc., etc. So yeah, and also there's probably coming up a Zig crash course and stuff like that. But anyways, for now, let's just try to focus on this guy. So CVKMim, awesome, thanks for the answer. You're welcome. Let's see, map VKR. So why not Odin? I didn't really see anything with Odin. Like I didn't see any advantage over something like Zig and Rust, etc. I didn't see any advantage there. There was one thing that I noticed is that they have good support for essential libraries. Like for example, Vulkan is actually officially included, I guess, in the standard library or something like that. And also SDL basically, or something. Yeah, it was something like that. And while that's very nice, and I'd like for other languages to inspire from that, because such basic libraries are like, it would be nice to have them in the standard library. Like, you know, just go ahead to the standard library and you're gonna find graphics libraries, etc. But I cannot really justify choosing to program in a language just because it have a library in the standard library. It just doesn't make sense. I mean, yeah, it is indeed painful to integrate libraries in other languages like Zig, C++, etc. But, you know, it's just a one-time thing. You're just going to do it once and you're going to forget about it, hopefully. So it really, I just don't see any advantage right now of Odin over the languages I'm using currently. So, yeah, int from bool. So what's this? I think it's timeout. Yeah, I guess it's a timeout. Where's the... There you go. So timeout is a timeout. All right, great. So here I'm going to say timeout nanosecond. Timeout, which is going to be a U64. Okay. And I'm going to say NS, basically nanoseconds. Or, you know what? Why not just do it? There you go. All right, let's go. Timeout in nanoseconds. Now the only thing that I would like to do here though is to make this optional. So basically if you don't want a timeout, then well, you could just say null here, meaning that you don't want a timeout. And so what I gotta do here basically is either timeout nanoseconds or else std.math, .math.maxint comtime t-type u64. And there you go. So if timeout nanoseconds is not null, we're going to use that. Otherwise, we're going to use maximum integer u64, which is basically practically no limit, no timeout. All right, so that's pretty much it. There's also, hold on. There's also one other edge case, which is that what happens if the timeout is 0. So they indeed said here what happens, but yeah, I think Zig is better for low-level C stuff and Rust for concurrency and safety. Yeah, concurrency is very, very easy in Rust. Also, of course, safety. So if you're working, for example, on a server, let's say a production server, then I guess I can see the appeal of Rust, and I can recommend Rust for such a project over something like Zig. So indeed, Rust do shine its own kind of projects, but in my own, hobbyist, low-level, and safe code, I would pick Zig at any time, basically. So as they said here, if timeout is 0, does not wait, but simply returns the current state of the fences. All right, gotcha. Makes sense. So basically, when timeout is 0, it's just going to tell you if the fences are in what state. Is it, I guess, timeout, or they're just idle maybe. But anyway, for now, I'm just going to actually just ignore that case for now. Okay, what's next? The init, wait. All right, so we got the fences out of the way, and I think semaphores are pretty much the same exact thing, kinda, almost. There's no wait though. And by the way, there's one thing that I forgot. Right. One thing that I forgot is, yeah, the init. We gotta initialize the fences. So I'm going to make that into, I guess, not sure yet, but I think I'm just gonna make it as a factory function in the device because it allows for more flexibility. Okay, so fn create fences. All right, amazing. Now that could return either an error or an fences, basically. Okay, so create fences. Let's see how we're gonna deal with that. Well, first of all, we need an allocator because we gotta allocate the array list. So yeah, create fences. Let's see. Right. What we also need, let's see. So let's try to use that guy. Self, well, we need self, of course. And let's see, self.dispatch.create fence. All right, let's see the actual stuff that this guy needs. Vacate create fence. And let me actually just revisit the registry. Let's see, vacate create fence. There we go. Oh, what? No, hold on. Vacate create semaphore. Okay. Vacate create semaphore. My bad. Right. So here you have device, create info, allocator, semaphore. Okay, let's have a look into the semaphore create info. Of course, just a structure type. Oh my God. I'm actually working with fences right now. Oh well, kind of got jumped up there. Why aren't you using comp times? It makes things blazing fast. I don't really need to for now. Just trying to make code work, and only use comp time when you need to. And there is indeed some drawbacks to comp time. You can't just use it everywhere though. Depends on the case. So, but anyways, device p create info allocator fence. So let's go to the create info. So you got an S type. All right. Be next flags. All right. Flags. There is one flag that is useful, which is signal bit. Specifies that the fence object is created in the signal state. Otherwise, it is created in this in-signal state. Now, the problem with create fence is that it only creates one fence. So let's see. Create fences allocator. So we could either accept an array list of vacay create, like vacay fence create infos, or otherwise we could basically like create one fence, and then if you want to create more fences, then you could just do that in the actual struct. What do you guys think? Let's see, vacay create fence. All right. So first of all, we need a device, I believe. So self.handle, and then we also need the create info. So basically info, and then we also, well, of course, an address to it though. And then we also require an allocation callbacks. So allocation callbacks. Okay, I just googled strings in Zig. Man, that is a low-level language, but at least you can ask for the length of a string char array. Honestly, I do like the simplicity of Zig strings. You know, just give me a bytes. Because, you know, strings are just very, very complicated. And it really depends on your projects, on how you want to deal with them. So just give me a some bytes, a buffer of bytes, and I just use them however I want. So for example, C++ tries to handle strings as some special things. It just blows it off. So yeah, there's just a lot going on with strings. So rather not put it in the language as a special case. Okay, so c.vacay allocation callbacks. Ooh, what I'm doing. What I'm doing. Hold on, remove this guy. Okay, so I think allocation and then finally it gives you fence. Well, fence. So you basically do it like this. So var fence is to simply c.vacay fence equal to undefined. And that's pretty much it. And then there's also, of course, the info, which, let's see, equal to vacay dot create info. Hold on. C.vacay fence create info. Let's go. Okay, and in fact, I'd like to use std.mem.init 0 init. There you go. Here you say c.vacay fence create info, and then here you initialize the stuff that you want to initialize. The core team guys even says Zig doesn't have string. Yeah, pretty much. There's no need for strings in the official language. That's a pretty good decision right there. Okay, so 0 init. Let's see. So first of all, of course, we need S type, and then there's flags. Great. So S type is equal to, let's see, c.vacay structure type fence create info. There you go. And then we also need, what else? We need flags, right? So flags is equal to c dot let's see, what is 0 init? So basically, if you don't use 0 init, you have to basically go ahead and initialize all the fields, even the fields that you would like to initialize to 0. But using 0 init, you can basically just initialize the things that you're interested into, the fields that you are interested into, and the other fields just goes on like 0 or null, depending on the type of that field. It would take basically the default value of that field. That's why I'm using 0 init here. So in this case, for example, I'm not specifying p next, so it's just going to initialize it as null, pretty much. So I don't have to go through all the fields and do that. In this case, it doesn't matter that much, since there's only one field that it is being automatically done for me here. But in like something like pipeline create info, that really helps when you have a lot of default values. So yeah, pretty much, hopefully that answered the question. Type, and then here, oh, what I'm doing, fence, and then create signal. There you go. So I'm basically going to have a signaled thing here. It's gonna be let's see, signaled Boolean value. So if signaled, then we're going to do this. Oh, what I'm doing. If signaled delta pi no string, I mean, if you have a good library, etc., then why not? I value transparency in a language well over convenience. I mean, yeah, sure, you go ahead and make your own libraries, but in the actual language itself, treat strings just as buffer of bytes, because strings can be very hard to actually do well, and it really differs drastically from one project to another on how you handle strings. So you just better not include it in the official library, but then just have some other people creating libraries for that, or in-home libraries for specific cases. For example, this string could be for fast development, this string for ASCII, this string for UTF-8, this string for God knows what. So you got the point. Alright, so if signaled, but if you force on your users a particular string, they're just going to, it's not going to be very interesting. So yeah, but like if you don't implement strings in the language itself, then you basically give the users the freedom to look out for some libraries that would fit them, or basically do it on their own, just using bytes. So yeah, pretty much. If signaled, c.vacate fence creates signaled bit, else null, else 0, I guess. All right, nice. So that's pretty much it. We definitely need a Zig crash course, surely, inshallah. So yeah. Okay, so that's it for that one. Now we need allocation callbacks too, and in fact we could just get them from here. It's pretty much the same exact thing. Where is it? Oh well. What? Where is it? Bruh. Create fence. There you go. Alright, allocation callbacks, and we also have an allocator, because in fact we do indeed need to create an array right now. So std.ArrayList and comTime ttype. Here we gotta give it c.vacate fence, and then here we're going to initialize it with the allocator, and there you go. Now we have two decisions that we could pick. Either when you create fences, you only create one fence if you'd like, basically, or we could too simply get a vector of signaled booleans or just a vector of vacate fence create infos. It's kind of hard to pick. Let's see. S-type flags create fence. Self.dispatch create fence. Let's see. Honestly, I think probably the best decision here, I guess, is to basically just create an empty array list of fences, and then you could basically add fences individually to the array list, to the underlying array. I think that's probably the best decision there. Create fence, or let's see, create fence. Init allocator. Okay, let me try one thing here. So instead of having this signaled allocation callbacks, let's see. Create fences. Signaled allocation callbacks. What do you think? What should we do here? Should we use an array list or add every fence at a time? Okay, let me try one thing. Okay, let's see. Turn on wrap lines. Oh, how? I forgot. Let's see, file or edits. I do remember. Where is wrap lines? Forgot. There you go. I guess that's word wrap, I think. All right. So I guess wrap words. Okay, let's go to the fences struct. I think what I'm going to do, too simply, I think I'm just going to have an fn init, really, to keep this very simple. And it would too simply have, let's see, it would just too simply initialize the underline array, I guess. So init self or an error. And then what we're going to do here, we're going to return dot and then handles. Ooh. Oh, well, honestly, go back. We could just too simply do this. All right, remove this signal and allocation callback stuff from here. We're just gonna have one allocator, and it would too simply return this, and it will return, where is it called? Oh yeah, handles. Oh yeah, I forgot. And by the way, you do indeed need allocation callbacks. Ooh. Or can't you specify it for each single one? I don't think that would be a good issue. All right, well, like leave allocation callbacks, I think, and let's just say oopsies, return dot, and here I'm going to go with allocation callbacks is equal to allocation callbacks. So okay, nice. And then also, let's see, the allocator is equal to allocator dot instance is equal to self, and also dot handles is equal to std.ArrayList. Comp time t type is, well, let's see, c.fence, vk fence, there you go, dot init allocator. Pretty much, I believe that's what's gonna happen there. Pretty much. Other than that, maybe we could add like a capacity later on, but anyways, so that's all what it does, what it's going to do there. And then basically we're gonna have an add fence there. So I guess fn wait, and then also fn add fence, and then we could too simply do something similar here. What's that period before each var name? It's just how you basically initialize the fields, which periods exactly. So create fences. Now here you're just gonna go with, I guess, void or an error, or it could give you the current fence, but I don't think that's really relevant. Yeah, that's probably not so useful. Okay, so you don't need to say the allocator now, and you only need to tell it, is it signaled? And also you need to tell it, yeah, that's pretty much it, I believe. Yeah, just signaled. And then here, fence, there you go, create fence. Well, here it would be self.device.dispatch. Allocation callbacks is self.allocation callbacks. The s type equal to the, yeah, s type, that's just how you create the fields in Zig. pretty much. That's just how you initialize fields. So yeah, like named fields. Okay, init the allocator. No, we don't need this here in this case. Okay, and we're basically going to say self.list, or oh yeah, handles dot add, is it, or append? Yeah, append, and append the fence that we have created, which is that guy. And of course, let's make sure to try that out. And that's pretty much it, I believe. So here we're creating a fence, we're checking if signaled. If so, we're gonna add this flag bit, else 0. And then we're creating the fence. And oh, this could probably error, so let's say vk map vk error. And by the way, feel free to actually contribute to this project in GitHub, especially fixing or just improving the current code. If you do add some more code, then we're just going to review it maybe, or do, I don't know, we'll see. But yeah, anyways, map vk error, create fence. Great. I think that should be good to go, I think. And here, instead of add create fence, I guess let's just say add fence. Pretty much amazing. I think that's how it should be. At least that's one design decision. There is one other design decision, but I think this is probably the most performant and the most straightforward. Anyways, so right now what we could basically do is, well, how to do that? Let's see. Here, before we show the window, so let's just create fences. So const fences is equal to self, well, actually fences dot in, oh, actually device dot create fences. And then here you give it the allocator and then the allocation callbacks, which is null. And honestly, I think I'm going to also put like a capacity there, maybe. Well, anyway, for now, that's just a little optimization anyway, who cares. So const fences, now of course that you need to try that out, I think. And defer fences dot dinit, and there you go, pretty much. Now we could too simply, when we want to wait for all the fences, we could say wait, and then we tell it if we want to wait for all the fences or just for one fence. And yeah, pretty much. And here we could even give it timeout, or we could give it null. Amazing, perfect. So now we're gonna add currently only one fence, I think, or we could go ahead and create multiple fences already. But honestly, I think let's just keep it simple for now and create just one fence for now. Okay, signaled. Do you want it signaled or not? For now, I guess false. I don't want it signaled. Okay, so that's pretty much it. And by the way, I'd like to just prefix this with is signaled. All right, lovely. Now, pretty much, I think the same design would be the case for semaphores. Just instead of c.vk fence, you would use c.vk semaphore. And fences and semaphores are kind of similar. They just have differing roles, basically. So handles, allocator, yeah, dinit, nice, destroy, semaphore. There you go. And then here, instead of vk fence create info, you have vk semaphore create info. And I believe there's nothing special here. Flags. What are the semaphore flags though? Let me actually have a look real quick. So vk semaphore create info, because sometimes there's some details that you could easily miss or forget. So I try to, as much as possible, to check out from time to time on the specification. Create info. Create semaphore, okay, and then vk semaphore create info. Let's go. What is the flags? Is reserved for future use. So currently there's no flags. Imagine writing this in Rust. Oh my god. We'd probably still be fighting with the borrow checker at this point. So yeah. that's what I really love about Zig. It just, and like over other languages, it doesn't come on your way. It's just plain simple. There's no hidden control flow. You just do you, and it just tries to help you as much as possible. It doesn't get in your way. No, you have to do it this way. No, you have to do it that way. Like, for example, there's no classes, and there's even no virtual classes in Zig. Like, for example, if you want virtual classes, you actually have to create structs of function pointers. It's like, for example, if you realize in allocator, so there is a general purpose allocator, but then if you want to use that, you have to get a stdmem allocator. Now, if you look closely into that allocator, it's just a v table and a virtual table, basically. So if you were to actually program an allocator in other languages, you basically create an abstract class, abstract virtual class stuff. But here in Zig, just like C, it's just basically a struct of function pointers. That's pretty much it. Pretty simple. Pretty straightforward. So yeah. All right. Wait. Well, where is it? Where we were. Okay, semaphores. Let's see. Vacate semaphore, destroy semaphore. Nice. How does debugging work in Zig? You can use basically VS Code. You could use LLDB debugger or GDB debugger, just like you would debug, for example, C and C++. But I still couldn't really figure it out yet on Linux. I did figure it out on Windows before, and in fact, if you go to my GitHub and you go to my previous project, Kodataku Image Viewer, this one, if you look into the .vs code folder, you're gonna find some files here, and if you have Windows, this would just work for you. You just gotta change some things, like for example the path to the executable, and like here you just gotta change it to your own executable name, basically your project name, and I believe also in tasks.json. I don't debug a lot anyway, but sometimes there are those cases where you need to debug it. Yeah, you really definitely need that, especially when you have a UB or something like that, or a segmentation fault or whatever. File location, auto detect. But luckily until now I didn't need that, but you could basically add those files if you are on Windows. I still didn't really figure it out on Linux yet, but when I need it, I'm going to look for it. Okay, what else? Now we got the semaphores. Now add semaphore. Or honestly, it's kind of weird. Why? Simply because, you know, like you already dealing with semaphores or fences, and you say add fence or add semaphore. It's already clear what you're going to add from the context. Or append, honestly. Let's just go with append, really. So let's go ahead and use that instead. Append function. There you go. It's very clear from the context what you're going to append. And here, of course, we don't need this guy. Semaphores are pretty simple. And currently it's just 0, so I could just remove this entirely. And of course, I should change this from fence to semaphore. Semaphore, okay. And I also like to always just infer from the context, so I don't have to change names every time. Appends handle, okay, lovely. And same thing here, instead of fence, I'm just gonna call it handle. It's very clear what kind of handle it is from the context. So there you go. Same thing with this info, for example. It's very clear that we're creating a fence, so why call it create info? Just call it info. It's very clear. Okay, amazing. Amazing. Append. Wait, now I just gotta change our code of the fences here. We got, instead of add fence, you just say append. Although it seems like here append false, it's kind of weird, but yeah. Okay, other than that, you gotta actually create a, instead of fences, now we gotta create semaphores. And by the way, I still didn't actually focus on allocators. Allocators are very interesting in Zig, but I just don't want to waste time on that right now because it's just kind of optimization basically. Only thing I wished for on Zig is multiple return values. Just saves time when you don't know how the implementation will look eventually. You could pretty much, I think, return an anonymous struct, which is any type, but then you lose out on IntelliSense. Or you could do simply create a struct. It's not that hard, so pretty much. I think, like for example, let me see, fn, like some function f, and then it returns some struct. And I think you could probably just do this if you really want to. And then I guess, you know, a f32 b, I guess. And then you return dot a equal to 1, dot b equal to 2, and there you go. That's how you return multiple values in Zig. By the way, there's even lambdas in Zig, but you do it in the same kind of manner. If you know Lua tables, they're just like this, the multiple kind of tool like that you could use for everything. That's kind of the same thing in Zig. You can use structs for everything. In fact, in Zig, even files are structs. Anonymous structs would be fine by me if the caller side can pull the values easily. Yeah, I think pretty much this probably would work pretty much. So yeah, or you could even say any type, I guess. You could probably even say any type, but then I think, I'm not sure. Anyways, structs are powerful, very, very powerful in Zig. All right, where we were, okay, try device.create. Well, I still didn't create that guy, and hold on, I'm going to close my window. Okay, back. Alright, let me see the chat. Okay, cool. Alright, what's next? Oh yeah, let's go back to the device. Where is it? Device. There we go. And oh, what's going on here? There you go. Well, go to device. There you go. And let's create a new function here. Now, basically kind of a similar thing here, but instead of create fences, you gotta say create semaphores. And then you to simply say self allocator allocation callbacks. Okay, great. I mean, yeah, pretty much. You just gotta change this guy. Vacate fence. Now instead of fence, we could go ahead and say vacate semaphore, right? And there you go. That's it. Pretty much same kind of thing. All right. Now, what's happening here? Fences, semaphores. Nice. Now instead of create fence, ooh, change this to semaphore. And by the way, the nice thing about Zig, you could even, for example, do something like this. Type of, I guess, you know, self dot, let's see, self dot handles, etc., or something like that. I guess you could say field, or, but anyways, right now we don't need that right now. So anyways, let's just keep it like that for now. All right, self.handle allocation callbacks handle. You cannot wait on semaphores, so I think so. Append dispatch, create semaphore here, and I believe that's pretty much it, I guess. So now let me just make sure to create a semaphore, or create semaphores, right? So create semaphores. Now give it the allocator and give it the allocation callbacks, which is in this case null. And now defer semaphores.deinit. Oopsies. And then semaphores.append. Well, we do not need this signaled. Okay, let's remove that. Oh, what the? Yeah, we don't need any. What? No, hold on. What the? What I'm doing? Let's go back. Oh, I think I didn't change one thing. Hold on. Create semaphores. There you go. I forgot to actually make this semaphores. Okay. So that was why. Now let's go back to where we have done that guy. Now semaphores though append. But that doesn't seem so good, honestly. Append. What should I call it? I guess maybe add or what? Append. No. Let me know what should I call this one. But for now, I'm just gonna keep it like that. Add. And honestly, I think I'm just gonna call it the same way here, anyways. So yeah. Concat. Not really. Okay, well. Add, because when you say append, you're inferring that you're maybe appending this object. But anyways, add false. It's kind of the same thing, honestly. But anyways. So that's pretty much it for that one, I think. Oh, in fact, you could basically maybe add. I mean, honestly, since semaphores doesn't take any parameters right now, but maybe they could in the future take some parameters. So no. So yeah, in the future they may take some parameters. Okay, well that's I believe pretty much it. Maybe let's see. No field named instance instruct main.fences. Let's see, fences. Oh, device. Okay. So device is equal to self, and then what else? And here also. Oh no. Where is it? There you go. Here should change it to device. Okay, what about now? Again, another problem. Expected type. Expected type U32 found cint. Where? Here, somewhere. If signaled else. Where exactly? No field name handle. Instruct main.fences. Ooh. Create fence. What? Let's see. Oh, self.device. Okay. Self.device, and also in semaphores, same thing, I believe. I think destroy semaphore takes more than that though. So yeah. And also dot handle. Okay. Self.device dot handle. Where is it? And I would guess probably the same thing here in destroy fence though. And you also need the allocation callbacks. Alright, so yeah. So something similar, I think, to destroy semaphore. And let's see now. Yeah, we still have that problem here. Consider using try catch. Oh, try here, and what else? I think it's maybe picking up on this guy right here. So maybe I could say, let's just say c.vk false for now. Let's see what's gonna happen there. And maybe the same thing with the other guy. Well, let's see. Oh, in fact, there's none there anyways. Okay, so what is the problem here? Cast discards const qualifier. Append. Oh yeah, because we're going to like mutate the object, we gotta say this. Hardest thing in software engineering, naming things. Perfectly right. It's harder than creating a Vulkan engine. Alright, error expected type. U32 found cint. Alright, so I gotta make sure to do the same thing with this guy. Add. Would this work now? Cast discards const qualifier once again. Oh yeah, var. Expected type U32 found cint. And consider using a try. Now here we have a little problem. Let's see. So expected type. So basically one of the fields, one of the fields in 0 in it that we have just added, expected type U32 found cint. Okay, let's see where we are using .0 in it in the new code. Okay, we are using it here. Doesn't seem like there's any integers there. Nope. And what about here? No, this is actually, we have already done that one. Interesting. Weird. Destroy. Okay, what if I've done as U32 here maybe, and then 0? Found cint. It's not telling me where it's coming from. That's the problem. And I don't think it's coming from here. Expected type. I mean, really? Extends. Key family index is U32. Semaphore create info. Create info flags if is signaled. Then pass in that, else 0. Well, I'm not sure this is legal to do, but maybe what I could do is to change this guy and see which field it's talking about. That's gonna be very hacky, but I mean, let's just do it, I guess. I'm changing the standard library now. Oh well, let's just do it. Log debug format, and then check for field.name. I don't know why I didn't add such a thing yet. Ooh, retry as sudo. Well, hold on a second. Okay, I think I've done that maybe. Come on, really? Weird. Hold on a second. Okay, I guess right now it's done it. Now let me try this out. How did you get started learning Vulkan? What would you say is the best way to learn it? I honestly don't know what's the best way would be. Hold on a second. It's still not logging in anything. That's stupid. Weird. Oh, without a specifier. Oh well, makes sense. So I gotta do this stupid thing once again. Oh my. Alright, hold on a second. Okay, let's see now. It crashes at compile time. Will we be able to see it at all? I think you could maybe see it using a debugger, not sure. But it's just Zig standard libraries fault right here because it's not showing me enough information to actually be able to debug the thing. Error expected type found cint. Weird. Oh well. Let me just revert this. Alright, let's just go back to our code now. Alright, let me just try the simple debugging here, I think. Copy paste that pwd. Alright, let's see. Fences, create fence. Okay, what happens if I don't actually use these guys? Sig build run. And it works, yeah. Alright, so which one is really the fault here? Let's see. Okay, so semaphores doesn't have a problem. Seems like. What about fences? Okay, here's the problem. Okay. What about this? So create fences doesn't have the problem. Alright, so what about this? Okay, so I guess it's right there. Okay, let me just add this guy too. All right, we have located the problem. So now let's dig into this. So the problem is right around here. Oh, hold on a second. Oh, why that's U32? Interesting. The fence create signaled bit is actually a cint, but the actual flags is U32. That's super weird. Why? This should be cint, I guess. But anyways, who cares? I think now I know the problem. So U32, okay. And let's go. They have saved the day. I have no idea how that goes like that, but anyways. Alright, so we have fixed the issue. Lovely. So first of all, you just locate the problem, and then you basically keep on collapsing. You try to narrow the problem space, the space where the bug is. Alright, well, anyways. Alright, add false, etc. Anyways. So now what we should do. Okay, I think right now we created this old school debugging. Exactly. So we created the create semaphores, we created the fences, and we added one fence and we added one semaphore. Amazing. So now I think we're good with that one. Next up, we have to acquire an image from the swap chain. So let's go to the swap chain and create an acquire image function there. So, oh, what the? No, not there, here. So let's acquire image from the swap chain. Acquire next image. And then here, I would just give you an index. It's gonna be U32. Isn't it? U32. Well, acquire next image. I would rather probably return usize so I could have a easier time with arrays later on. But anyway, so acquire next image. Let's see. So now self. Well, we need self. We're gonna need some other stuff, but let's see. So self.device, isn't it? Dot extension. Oh yeah, dot extension dot device dot dispatch dot, let's see, acquire. Oh, actually no. Extension dot dispatch dot acquire next image. Let's go. And let's see right now the signature of this guy. So we need the device, all right, great. Let's see. So we need the device, which is basically self.device, oopsies, well, self.extension.device.handle. Let's go. And now the swap chain KHR, which is basically the handle of the swap chain. Now, one thing is that even the swap chain, we're gonna need those handles. Like, there is some functions that handle swap chains, like, you know, in bulk, but I'm not sure yet how to deal with those. It would be nice if, like, I do have an idea, which is to basically use SOA, I think. I don't remember the name exactly. There's two relevant names. Hold on. Structure of arrays. Oh yeah, so there is structure of arrays and arrays of structures, basically SOA and AOS, I believe. Yeah, exactly. So maybe I could make use of this to actually, and there's a pretty cool thing which is called multi-array list in Zig, which could do the job for us. I'm not sure if how that would go. Like, basically, But let me first of all finish this up. Hold on, let me just finish this up first. So self.handle u64. Where's the u64? Acquire next image. I think it's probably the timeout. Let me make sure. Okay, there you go. Vacate acquire next image. So it's timeout, right? And then semaphore and fence and timeout. How long? If no image is available. If no image, specifies how long the function waits in nanoseconds if no image is available. Interesting. If, hold on a second, has been created. Forward progress, what is even that? Come on. The Vulkan spec file is like, even my browser can't handle it. How do you want me to read it all? Look at that. This is the Vulkan spec. All right, let's see. All right, I think I should probably read this stuff off camera, but right now let's just make it work. Okay, so anyways, acquire next image, u64. So u64 is the timeout. I think I'm gonna do basically kind of a similar thing here. So timeout, nanoseconds, and it's gonna be an optional u64, and basically if timeout, oopsies, if timeout nanoseconds, right, then we're basically going to say, oh, actually no, not this. We're gonna say timeout nanosecond or else 0, no, cd.math.max int, and then u64. There you go. And vacate semaphore is basically self.handle, and vacate fence. Interesting. So this actually requires one fence instead of, is it? Yeah. And what is that? Interesting. Hold on. Acquire next image, vacate fence. Can get a semaphore, a fence, and an image index. Oh yeah. A semaphore, a fence, and an image. But hold on a second, really? Oh, that's semaphore. My bad. So we could basically give it a semaphore. Interesting. All right, sure. So semaphore. Then here we're just gonna get a vacate semaphore, and then we're gonna need a fence. But of course these are optionals. So vacate fence. There you go. As you can see, they're optional by default since they're from C. Explain that or else. Or else, basically, if you're coming from Rust, it's basically in wrap in an optional. So here, basically, timeout nanoseconds is an optional of u64. So timeout nanoseconds or else max int u64. Here, what I'm saying is that if timeout nanoseconds is there, it's not null, then we're gonna take that value that we got there. Otherwise, if there is no value inside that optional, then we're going to give it maximum integer of u64, too simply. And here we got the semaphore, and here we got the fence. And here this gives me the index, the image index, but yeah. const in wrap or exactly. If you're coming from Rust, that's exactly in wrap or index var index u32 in defined, and then we could basically pass in that index. There you go. Now this could fail, and this also can yield, which basically means can stop execution until the next image is ready, which is governed by this timeout nanoseconds. But anyways, let's see, self.extension.dispatch, acquire next image. Now what I could do, I should make sure to map this vacay error. Thanks for the person who recommended for me to enable word wrap. It's kind of confusing sometimes, but it's very useful, so I don't have to always zoom in and out. And but anyways, try map vacay error, and let's go. Now we're just gonna return the resulted index. Pretty much amazing. Now we do need to actually handle one success result, which is, what is it? There you go. This suboptimal and this not ready in timeout possibly. So we have to look in for this one later on, but for now I'm just gonna ignore it. Okay, acquire next image. Okay, great. Now we also need present, I think. QPresent. I think that should be on the device, no? Well, I think so. But anyway, let's go back to the here. Okay. Now here we're going to get the image index. But honestly, hold on, no. Why the image index? Hold on. So, but anyway, let's just go ahead and do this swap chain, and we're just gonna change our stuff dependent on the use case. So acquire next image, and then here you need timeout nanoseconds. I don't care. Semaphore, I do care. So I'm gonna say semaphores, and I'm probably going to say dot, let's say get 0 or something like that. Okay, and then fences dot get 0, for example. So basically we want to get the first fence. So let's actually go ahead and to the fences, and let's create a new function, fn get, and you basically get usize, I believe, yeah, index usize, and then it would give you back c.vacay fence. Now it would just return self.items, oopsies, well, self.handles dot items, and then here we would say index, too simply. Use of and declared identifier self. Yep, self, and there you go. Nice, lovely. And that's pretty much it. Otherwise, maybe we could get, is there like some function to actually get it from the array directly? Hold on. Doesn't seem like there is get last or null, but that's not relevant. So we're just gonna say self.handles.items dot 0, index. Kind of a similar thing for the other guy. That's just a helper function, really. In fact, most of that stuff is helper functions anyways. So get, and here pretty much the same exact thing. Nothing changes except for this guy. And that's pretty much it. So right now we only have one fence and one semaphore, but later on we're gonna be implementing some in-flight frames. So we gotta actually use an actual index. But anyways, whatever. So that's pretty much it for acquire next image, although we have to revisit that function later on to handle an edge case, or in fact some edge cases. But anyways, so right now we should be getting the image index. Next up, we would probably need to present the image. Let's see. And also we gotta wait. So how to wait? Swap chain, I believe. No, actually fences. Okay, fences dot wait for all. For now, go with false, I guess. Timeout seconds. Well, honestly, coming to think about it, you may want to wait for just a portion. Hold on. Yeah, honestly, you may want to just wait for a portion of fences. So we should probably use a slice instead of an owned array. Yeah, I gotta restructure this. I didn't think about this before. But anyway, for now, this should be fine, I guess, for now. And then, so we're basically waiting for the image, I guess. So fences dot wait for all false. Timeout nanoseconds null. Great. Now we gotta actually present that image. And for presenting an image, you gotta go with the queue. And we don't have a class for a queue, but we have a class for a device. So we gotta add it here. Or otherwise, we could honestly go with the with maybe the swap chain. Yeah, I guess maybe that would be better, I guess. Okay, we'll see how that goes. I don't think so, because I think queue present actually takes in multiple semaphores, but anyway. So yeah, fn present. Let's see, here I think it should be, not sure, I think void. Select all, then word wrap. What are you talking about? I have word wrap on, so I don't know. So present. Is word wrap actually line wrap? I'm not sure. I don't know. But I could only find word wrap though. So, okay. Let's say now self, of course. Now let's see. Self.device or what? Extension? Yes, the device.dispatch. Present or what? No. Oh, I didn't load that yet. Okay, hold on. Let's go to the dispatch. Let's add a new function. So we're gonna add c.pfn vk present image q present, right? Q present khr. That's the one that we need. And let's see. There you go. Some lines aren't wrapped though. I'm not sure why that's the case. So okay, so Q present. Oh, this is actually shouldn't be here. It should be on the swap chain extension, I guess, isn't it? Yeah, probably swap chain extension. Oh, we already have that there. My bad. All right, let's go where we were. Okay, I already added that, interestingly. So it's inside the extension dispatch, I guess. So q dispatch, oopsies, well, dispatch.q present. Let's go. And let's find out the stuff that this guy needs. Now it needs a vk queue, and it also needs a present info. Now here's what I was talking about before. Present info, I think it is actually word wrap. Weird, since word wrap is actually usually something else. Yeah. So present info khr, it takes a type. Can't set it for the editor word wrap. Yeah, I already done that through the GUI. So anyways, wait semaphore count and p wait semaphores. P wait semaphores. Okay, p wait semaphores. Interesting. yeah, I honestly gotta redesign that thing. I kind of have had some assumptions. It doesn't really matter that much, but anyway. So swap chain count, as you can see, it takes in an array of swap chains. Although currently we only have one swap chain, but it would be nice if we can design on about this like already. So in if we need that, we would have less work to do. So image indices. Here the image indices that you'd like to basically present, and then pre-results for every swap chain. All right, interesting. Because basically you gotta do as much as possible in a batch in Vulkan, basically. So you would like to present as much swap chains in one, in one go, basically. But for now, I'm just gonna assume that we're just gonna go with one swap chain, I think, to simplify this for now. But later on, when we get something working, I think we could change it. Word wrap column. Word wrap. Oh, hold on. Line wrap. Bounded. Word wrap column. Oh, there you go. I think that's it. Okay. Well, let's see. Honestly, present, dispatch. I mean, yeah, well. Anyway, for now, let's just do one swap chain. Who cares? Q present. Let's see. Q present KHR. You need this, guys. All right. So let's go back to Q present. Okay. So here we need the queue. So self.device.queue. We only have one queue though right now. So self dot, let's see. Extension, right? .device.queue. And then here we need the info. So an address to the info. Let's go const info. Let's see. And here we could basically use a cd.0 init or init0 mem.0 init c.vk q present info. No. AKQ. What was it again? Present info. Okay. That's kind of inconsistent, but fine. Present info KHR, let's go, and then here, and then, of course, as always, S type. Now CVK structure type, present info KHR. Maybe it needs the file reload to fully work. File reload. Okay. Is that it? That's too small though. But anyway, where is it? Where is it? Or should I say too big? But anyways, depends on how you see it. Well, where is present? But at 80, I think dynamic should be on. Settings. Dynamic. And the value is set to on. This. Light decay. Anyways, let's go back. Present. Now Q present. Okay, well this could fail, so let's go ahead and say map vacay error. Map vacay error. So Q present. Oh my god, it's weird. Anyways, present void. Does this return anything? Vacay result, just that. Okay, so that's pretty much it, I believe. Well, I forgot to actually fill this guy, so let's actually grab this guy, put it around here, and let's see. So what we got? We got wait semaphore count, and that would need semaphores, I guess. So I would need the semaphores. Oh well, I should probably use that SOA, I guess, or struct of arrays. Yeah, SOA. I think this would fit perfectly here. But yeah, we'll see later on. Okay, so semaphores. I never really used that one before, but I think this would perfectly fit this problem of still having control, like still having like an object-oriented interface, but inside you just have arrays. Like for example, you would have an array of handles, and you could too simply just pass it directly to such functions that takes in stuff in bulk, basically. But yeah, anyway, semaphores, and then we have fences. Fences, so wait semaphore count, it would be basically semaphores dot, I guess, handles dot len, oopsies, well, dot items dot len, it seems like, and then the wait semaphore, let's see, infos or what, semaphore, oh yeah, p wait semaphores, okay, is equal to const vacay semaphore. Well, basically semaphores dot handles dot ptr items dot ptr. There you go. And by the way, I should actually make this u32, I think, as u32. And in fact, I believe I would need an int cast here. There you go. Now the same kind of, or at least a similar thing for swap, well, swap chains, it would be for now just one swap chain, but I really would like to design this very nearly, but as soon as possible. But anyways, so swap chain counts for now 1, and then swap chains would be equal to const vacay swap chain khr. In my case, it would be just self.handle. And p image indices, it would be for now Oh, it would need the index. Interesting. Ooh, interesting. I have a little idea. I'm not sure how it would go, but anyways, for now it's fine. Okay, so image index. For now, you just gotta actually get the index of the image. So it would be U32. Okay, p image indices, and that would be that. And then you also need, I guess, oh, the count is inferred from, I believe, the swap chains, maybe. Yeah, I think so. Why are you casting it? Because with semaphore count is U32 and items len is usize, so it should be converted into U32, but then you have an error which says that you're doing a narrowing conversion because usize is bigger than U32. So you have to explicitly tell it that it is fine to narrow cast. So you have to add int cast there to basically acknowledge to the language that I know that I'm doing a narrow cast here. So yeah, exactly. So that's pretty much it, I believe. Swap chain, self.handle, index. That's for image indices. Swap chain count, b wait semaphores, wait semaphore count. And yeah, I think that's it. Yeah, I think that's it. So let's actually try this out, I think. For now, I'm just gonna do before the wait, I guess we gotta say swap chain dot present. There you go. Here you give it the semaphores and the fences. Oops. Where's the semaphores that I created? It's not helping me out here. But anyways, and then here we got the index. Index is 1. Oh, index is here. Image index. Let's go. Alright, I really need to redesign this. Really need to redesign this. But anyway, expected type U32. Try. Oh, what? Already trying it. Okay, found type of. Int. What? Are you sure it's in this line? Oh, my bad. It can error. Okay. Consider using a try catch. Try here. I always forget a try. Try here. And probably try here. Isn't it? Yeah, it should be like this. So let's go back. Try this. It's always a try. Alright, no field named len. Makes sense. Items.len. I probably gotta cast it, but let's just run anyways. And there you go, it's telling me that. So I should use int cast. Now before I used as and then used int cast, but here Zig already know that I want to cast it to U32 from the function signature. And let's go. But we have a little problem that I forgot, which is to reset the fences. To reset the fences, yep. And now everything is blocked for me. Alright. Good. Now let me make sure to actually go ahead and fences reset. Oh wait, they still didn't do a reset there. fn reset self, and it may fail, I think. And then we could simply say map vk error self.device. Ooh. Is there a problem with the stream? Hold on. Is there a problem with the stream? YouTube is going crazy. YouTube is not receiving enough video to maintain smooth streaming. Is the stream fine? Is the stream quality fine? Let me know. Okay. Device dispatch dot reset fences. Yeah, I had to click on live again. Alright. Because it just blocked for a second because I forgot to reset the fences, I think. Alright, nice. Reset fences result. Map vk error. Yeah, just a quick cut. Yep, makes sense. Reset fences here. So we got vk fence device. Okay. So basically, where is it? There you go. So here we gotta give it a self.device.handle, and then we gotta give it the self.handles.items.len, and then we actually gotta int cast it once again. And then we also gotta give it the handles.items.ptr. And there you go. And let's try this out. Oops, hold on. Where I'm using resets. Am I using it even? No. Okay. Try fences.reset. And yeah, we got a black bin window. But as I said, I'm really not satisfied with the design that we have done for this. I kind of assumed some things, but I think I know right now the right design, but I gotta experiment though. So you app stole the screen and didn't give it back causing OBS to glitch. Kind of. Basically my application drained all the resources because it didn't reset the fences. So yeah, pretty much. Let me actually go ahead and run vk config. Let's see. vk config. Let me make sure there's no validation errors, I guess. There may be. Well, there is. Okay, let's see what the validation error is saying. Okay. Images passed to present must be in layout. vk image layout present src khr. Ooh. Or image layout shared present khr, but it is in image layout undefined. Each element must be the index of presentable image. Layout present. Okay, I think, hold on. I do remember there was like a usage kind of thing. Let's see, image layout. Ooh. What? Well, how I'm supposed to actually make it that? Oh, I see. Now, if we were using a render pass, it would basically does that job for us, but in our case we don't have a render pass yet. Otherwise we could use a barrier, but we still need a command pool, etc. But yeah, what else? Is there anything other than that? There is this one. Cannot call vk destroy semaphore that is currently in use by command buffer. The Vulkan spec states all submitted batches that refer to semaphores must have complete execution. Interesting. So I gotta actually do something here. In fact, I gotta like before removing the device, hold on, let's go to the device struct. Okay, before removing the device, where is it? Dinit. Before that, we have to make sure to call some function, which is called, I don't remember. Let's see, wait for, no. Let's see, queue wait idle. Okay, let's say vacay idle. Okay, there's queue wait idle and there's device wait idle. Display power, get image view handle. So we could use get wait idle. So let's go ahead and do that, I guess. And that may fix it. May, not sure. Let's see. And what I'm doing, wait device wait idle. Damn, Vulkan is a ton of work just to set up a window. Insane. No, the setup of the window is actually being done for us by SDL, but the rest, the actual rendering to the window, is what Vulkan is going crazy with. In the find. But I get what you're talking about. So device wait idle. Now, before destroying the device, we have to make sure that it have finished. I think. Let's see. Device wait idle. And what's that? You could give a vacay result, interestingly, and then a vacay device. It takes a vacay device. Okay. So here we gotta say basically, ooh, I cannot really return an error, so. But maybe honestly I would make an assert just for debugging purposes. So debug.assert. I don't think returning errors from a dinit function is a good idea, but asserting could be fine, I guess. Oh, what I'm doing here, not the okay dot equal to, well, or actually not, well, it should be greater than or equal to c.vacay success, basically. And yeah, now here I could basically give it the handle. And let's see how that would go. And no, that didn't fix this error, but indeed we did have to do this anyways. But let's try to see how that would go. Cannot call vacay destroy semaphore. On vacay semaphore that is currently in use by a command buffer. That is currently in use. So somehow we're, but how do you actually wait for it? Let's see. Well, where we're actually quitting though, I think we're basically quitting in the event loop, right? Break main loop. Maybe we should actually continue. Alright, let's see if this actually would fix this. Hold on. What happens if I say boolean is running, for example, is equal to true, or let's call it should close, okay, equal to false, right? And then while not should close, you could too simply say should close equal to true instead of just breaking out of the main loop. And let's see if that would fix it or not. Let's see, should close. How do you actually, should close equal to true. Oh, oh, I see. So that should be a var, right? Let's see. Nah, that still doesn't fix the problem. Interesting. But anyway, for now I'm just gonna ignore those errors. But yeah. So try fences wait and then reset. Or honestly, oh, hold on. Where's that device wait thing? Where's device wait? Wait for idle? What? Device equals struct. Oh, I see why. Okay. What happens if instead of doing that there, honestly, can we just do it here when we actually want to break? Hold on. If I do... Ooh, what the... Okay. So what happens if I actually do this, right? And then basically before breaking the main loop, I do device dispatch, device waits idle, then device.handle. What would happen then? Would that fix it? Yeah. Oh. Yep, that fixed it. Okay, nice. So basically we have to actually wait for the device to become idle. In fact, not in the device, but you know, before quitting basically. Why? Too simply because what happens is that we actually destroy the swap chain and defenses, etc., before destroying the device. So that's why it happens. Hydrate. Yeah, I gotta take a little break and I'm going to come back. Just 5 minutes and coming back. Okay, back. That's probably less than 5 minutes, but let's go. Okay, well. So is there any questions so far before we start on the next thing? Present, wait, reset. So So in fact, I'm going to actually, and since we put it here, it doesn't matter if it's success or not, honestly. Okay, let me actually make a little helper function for this guy. Let's see, vk fn wait for the or just wait. Wait idle, or let's see, device wait idle. Okay. Wait idle. Okay. And this could be either an error or that. Now I could just simply say vk mem, or what I'm doing, map error, map vk error. Let's go, and then basically put that there, and there you go. Use of undeclared identifier self and self. Let's go. Nice. And now, instead of device wait idle, what we gotta say is device dot wait idle, and maybe we could try that out. And there you go. Consider using a try. Oh yeah. Or can't we just return? In this case, let's just return it. There you go. Alright, and it's working just fine. Now resizing, we're still not handling it correctly though. There you go. We have a problem with resizing, but I don't want to deal with resizing for now, just yet, until we have some rendering going on, because it can be hard to notice what is the problem when you don't, when you're not rendering anything. So yeah. Okay, pretty cool. Pretty cool. Now, as I said, I'd like to actually experiment with one particular design that may be useful, which is array of structs. Now this is actually, hold on, struct of arrays, actually, struct of arrays. It's called SOA. I never really used it before because I never really needed it, but I think right now this may be useful in my case. And I think I'm going to actually use it, let's say, for example, all right, let's see. Now, if I said std.mem, no, actually, no, multi-array list. So there is something called multi-array list in Zig, which is quite interesting. You give it a type, and then like you give it a struct, and then it turns it into an array of a struct of arrays, which is quite crazy, you know. So multi-array list stores a list of a struct or tagged union type instead of storing a single list of items for each field of the struct or list of tags and bare unions. If the struct, okay, cool. Okay, let's try maybe to use that with fences. Let's see if we can redesign that. Okay, so we have handles, which is an array list, and then we also have a device. We have allocator and allocation callbacks. Actually, that may be useful for swap chain though. Let me see. Let's see, swap chain. Where's swap chain? What the? Okay. So here it has a handle and then swap chain extension. This could be used by multiple, I think. Well, okay, anyways. Allocation callbacks, allocator, images, views is retard. Okay, let me see. Let me have a look. So what if we use that with swap chain? Okay, what's gonna happen there? So this would give me a type. Let's call this, for example, swap chains. So this is an actual type. Okay. Now let's try to figure this out. So I could too simply, for example, say get, I guess. No, there's another one called shrink and free, shrink retaining capacity, slice, sort span. Hold on, let me actually read something about it. Zig multi-array list. Structure for arrays, there you go. Okay, let's see. So for example, you have a monster, then you can have a monster list. And oh yeah, items, it's called items. So you could say dot items, the self, which is, well, it needs to get it from its own, isn't it? Oh, well, we need to first of all, I guess, create some swap chains first. So basically swap chains, I guess, is equal to swap chains dot init, or what? Oh, how we done it? Hold on. Monster list. I guess you just do it like this. Weird. But okay. And then you could basically say swap chains dot items comp time field, and here you could actually use dot handle, for example. And then you would basically get the array of all the handles. But you could still do swap chains dot get 0, I guess. Then you could just use 1. Honestly, that's very interesting, but I think it's kind of hard to incorporate it into the existing stuff right now. So I think I'm going to use it on command pool and command buffers. Maybe that may be useful. Let's see, swap chains, command pools, command buffer. Yeah, I think so. All right, let's go ahead and create a command pool and the command buffers, or command buffers. All right, so let's go ahead and do that. So const struct, well, command pool. Well, first of all, we need the command pool. And the command pool, what it needs. Well, let's actually load the function pointers that we need. There you go, the device. Now let's actually load the function pointers that we require. So pfn vk create command pool. There you go. We need that one, and well, it's gotta be like this. And then vk create actually destroy command pool. There you go, and then we basically require allocate command buffer. There you go, command buffers. And here I'm going to call this, I guess, allocate command buffers, isn't it? Allocate command buffers. Great. And yeah, I think that's it for now, isn't it? Here, destroy command pool, and I think that's it. All right, let's go back now to the const pool. Oh, we didn't create it yet, or what? What the? What? What's actually go down. There you go. I don't know why I didn't find it before. Okay. So here, if an init, just like before, self, and then const self is equal to this. Alright, init, self, and then the init. It's gonna take self, let's go, and here basically void, let's go. Amazing. And what else? Do we really need the... I don't think. That's super weird, but okay. Now we need handle, which is gonna be a c.vk command pool. Oh, I need the struct. Okay, well that makes sense now. And then we need the allocation callbacks. And yeah, and probably an allocator too though. Not sure, we'll see. Alright. Allocation callbacks, allocator, init. And would probably hold command buffers. Oopsies. Oopsies. Okay. Let's just get rid of allocator for now. Anyway. So now let's just say in the init function, or actually let's actually create the command pool from the device. Okay, let's go ahead, const device is equal to struct. Bruh. There you go. Okay, well, let's actually create command pool. vk create command pool self, and then here you would basically give it command pool or an error, too simply. And now what we're gonna do, we're gonna map, I guess, vk error, and then I'm going to say self.dispatch dot create command pool, and now here, and amazing ZLS, it's telling me that's weird. Okay, create command pool. Oh well, let's see now. Const fn, so let's just copy this over and let's figure out how that works. Create command pool. There you go. So here you need the device, which is basically self dot handle, right? And then command pool create info. Okay, so that's info, and then the allocation callbacks, which we could get basically. There you go, and we could put them here. And then finally we're gonna get the command pool. Nothing fancy here. What's gonna be interesting is the actual allocation of command buffers. So const info is equal to, all right, let's see. So info, how can it do that? Well, command pool create info, and let's see dot. Oh, let's actually use that stdmem thing again. 0 in it. Comp type c dot, let's see, info or what? Command pool create info. There you go. Dot, and now let's just see what we got here. So we have an S type, and we have flags, and we have key family index. Okay, key family index is the most important. Flags are also interesting, but we'll see. So first of all, key family index is equal to, well, we already have it, I think we're inside of the device. So self dot q, let's see, q, actually not q, q family index, I think, or adapter, right? Key family index, let's go. Nice. If we ever want to use multiple queues for multi-threading, we gotta redesign a lot of things. But anyway, it just makes a lot of things much harder to deal with if you don't already know how you're gonna be using it. So okay, key family index. And what's next? Flags. Now flags, there is some interesting flags. Command pool, create. Okay, there is transient, there is reset commands, and yeah, reset command buffer bit, reset command buffer. Like, I think if you want to basically, actually I think the best way to do this is to simply go ahead to registry, and let me see, Vulkan. There you go. And now let's see the flags, and there you go. There's transient, reset command buffer. Or freed in a relatively short time frame. This flag may be used by the implementation to control memory allocation behavior within the pool. Now we're going to be allocating command buffers every frame and then resetting them, I guess. Well, for our case, we could indeed go ahead and use, just create the command pool once and just reuse it. In our case, if we want just static stuff rendered, but we would like to change some stuff every frame, like the color, for example. So I would go with this one. And then there's also create reset command buffer bit. Allow any command buffer allocated from a pool to be individually reset to the initial state, either by calling reset command buffer or via the implicit reset when calling vacate begin command buffer. If the flag is not set on the pool, then vacate reset command buffer does not be called for any command buffer allocated from that pool. All right. I may need these two flags really, but we'll see. For now though, I'm just gonna set the flags to 0, honestly, until we need them, until validation tells us about them, too simply. And of course we need the command pool now. Well, it's gonna be just a handle, right? So c.vacate command pool is equal undefined, and now we could too simply say handle here. Nice. Okay, well, what's next? Let's return. So device, I believe, needs that, and then I'm gonna say self, and they're also gonna need allocation callbacks, which is basically allocation callbacks, and also gonna need handle, I believe, which is handle. And there you go. With that, we created a command pool. And we do need the device, so what I'm doing, device, there you go. And now in the deinit function, we could just say self.device.dispatch. Let's see, destroy command pool. And here we probably need to pass in self.device.handle and then self.device, actually self.allocation callbacks. Oh no, handle first, then I think allocation callbacks. And there you go. Of course that can't fail. And now let's try to make a command pool. So const command pool is equal to command pool dot device dot create command pool, allocation callbacks null, and let's go. Now of course defer command pool dot dinit. Oopsies, there you go. And that's it probably for the command pool. And as always, I always forget about these. Also this. And there you go. So I think we're creating that guy now. Parameter S type. Ooh, I forgot about the S type. Interesting. Create command pool. Where is it being used? There you go. So I forgot about the S type. C.vec structure type command pool create info. And let's go. So now pretty much we have created a command pool. Now next up, and I guess this is the fun part where we're, well, not fun, but we get to experiment on the new design that I'm thinking about. I don't know, we'll see. So let's see how that would go. Well, basically const command buffer is equal to struct, yes, and it would basically contain a handle. Right. Well, there isn't a lot of moving parts here, I think. And not sure, we'll see. Let's see, fn allocate. And it would give you, well, it would give, I think, a slice of command buffers. Well, let's see. So we gotta need to allocate. Allocator is equal to self dot location or what? Mem. Oh, let's go. And how we're gonna deal with that? Okay, self dot device dot dispatch dot allocate command buffers, and again, as always, try map error do this, and we probably need first of all the device handle, and then we probably need allocation info. So const c.vacate allocation command buffer allocate info. Let's go. And let's see, command buffer count, command pool level. Next, command pool, we already know what it is, which is self.handle. Next up, we have the command buffer count, and oh, I forgot about the S type again. C.vacate structure type allocate info. Oh well, command pool. Oh, command buffer allocate info. Let's go. And as always, I'd like to put the S type first, and then level. For now, we're not going to be using secondary command buffers, so the primary command. Ooh. command level primary. Okay, let's go. And the other thing is command buffer count, which is, well, just how much you want to allocate. Count. Okay, so count would be 32, I would guess. And there you go. Alright. Now you probably have to put that somewhere. So pfn vk allocate command buffers. Alright, so you need the device and then the command buffer allocate info, then command buffer. And here it's probably a list of stuff, like an array. Alright, interesting. Well, we gotta allocate memory. Although, well, anyways. So, okay. So const allocation is equal to allocator dot allocate, well, dot allocate alloc, right? C dot vacate command buffer, and the end size is, well, count. There you go. And then error defer allocation dot free, allocator dot free allocation, and let's go. Now we got that out of the way. Next up, it would be to give it the info address and then the allocation PTR. Isn't it? Oh, try. And finally, you just return the allocation, which is basically the slice of command buffers, but it actually would be just normal command buffers though. Let's see. Interesting. Command buffers. We could make an extern struct just to make sure. Well, interesting. Okay, I guess we could make sure to do extern, I guess. And so we make sure that it is the same as cvk command buffer. And with that out of the way, what we could do is just allocate command buffers, I guess. I never done this before, but I guess maybe that should work. Allocate command buffers. So it needs vacate command buffer. Okay, great. And you'll see why I want to do this in a second. Where is it? Request device. Okay. Go back to allocate. There you go. Alright. I think it would error here, but we'll see. Okay, let's try to create those command buffers, or allocate those command buffers. So command buffers equal to command pool dot allocate how much command buffers you want. In my case, for now, we're just gonna go with 1, and then allocator. Oops, and we do not have a defer. You know why? Because, well, when it comes to allocate, instead of create, the moment you actually destroy the command pool, you automatically deallocate. It's kind of like a, what is it called? Hold on, cd.heap. Arena allocator. Yeah, it's kind of like arena allocator. You know, the moment you destroy the actual host objects, which is in this case command pool, all the allocations becomes invalid. You shouldn't use them anymore. But the problem is that we should deallocate the buffer, like the buffer that is holding this guy. Oh, well, it's quite easy. Just for, yeah, I almost forgot about that. So free command buffers. So here I'm not freeing the command buffers themselves. I'm freeing the array that actually holds those command buffers. Okay, pretty cool. Pretty cool. Let's see if this actually works. I think it would error. And let's see. Missing struct field p next. Oh yeah, I forgot about that one. So you could just say cd.mem.0 init, put in that guy there, and then put this, put that, oops, hold on, put that there, and there you go. And we have a problem here now in the free function. Oh, we gotta try that guy. Well, where is it? Command buffers. There you go. Try to allocate. And cannot cast into. That's the error that I was expecting. So I need to basically tell it to just cast it, because I know that this is fine as long as command buffer is the same as, you know, it's like this struct is kind of like just a wrapper over handle, so I can do something that I'm going to show you in the future. But let's see if this actually works. I guess maybe PDR cast. Alright, seems to be fine, which is nice. And for now, just so, because it's littering everything with those swap chain errors, for now I'm just going to comment this out for a second. Okay, so as you can see, there's no warnings for that one. Alright, amazing. So, and there's no memory leak. Well, at least in the happy path. But in the sad path, which when an error happens, I probably have forgot some error defers in a lot of places. So I gotta revisit the code in a second. But probably I gotta do that in off camera. That's not a very interesting thing to do. So anyways, defer allocator.free. And now we got the command buffers. Now what's interesting about this now is that I could, well, I need some functions first. I need to load in some function pointers. Const device equal to struct. At this point I need a minimap. Well, not this minimap, I mean I need some waypoints. But anyway, I gotta actually split this up into files, but anyways. So, what's next? Let's see. So let's just copy this guy. Right, now let's see, std method child. Ooh, OFV. PFN, VK, CMD. Okay. Oh, I forgot about this one. First of all, I need to begin. What is it called? Oh, begin command buffer. Yeah, I forgot about this one. And then begin command buffer. And then end command buffer. I think. So, or it may be something different. Yeah, it's fine. So that's it for that one. And now there's also now basically what we use command buffers for is to send commands to the GPU. Now here's an interesting analogy that I'd like to always think about, is that, you know, the distance between the GPU and the CPU are like, is very large when it comes to the electricity speed. So, you know, like for example, when you have a truck, you know, you have some commands or some goods in this scenario, or some boxes, for example, and you want to actually deliver them to another city, what you gotta do? Well, you just take one command at a time, deliver that into the other city, or deliver one box at a time and then deliver it to the other city, then come back to the other command and deliver it again. That's gonna take years. But what you should really do is to load as much commands as possible in that truck, as much boxes as possible that you can hold and that you can send and that are available right now, as much as possible, and send them in one go, in one batch. That's why we need the command buffer. You keep on batching commands on that command buffer, then you send it once through the queue to the GPU, pretty much. Hopefully that makes sense. And we're using a command pool, or when you see Vulkan using a pool in general, it means that we're gonna be allocating, in this case we're gonna be allocating a lot of command buffers frequently. That's why we need the pool, because if we were to create a command buffer every time, that would be very, very costly. Not a good idea. So we're using kind of an arena allocator there. That's what a command pool is. But anyways, so now we can actually load function pointers for the commands. So let's see, every function that starts with vkcmd is a command. So I guess I'm going to start with, well, I think I probably need the pipeline memory thing, or don't remember. Barrier, I guess barrier. Memory barrier or a pipeline barrier, one of them. Pipeline barrier probably. Okay, what else? There's this guy, barrier 2. Okay, just barrier, vkcmd pipeline barrier. And this one by itself is not very interesting, so we're gonna add another one, which is let's see, I don't remember the exact name. I guess it's fill buffer? No, don't think. Color, blend attachment, clear. Oh, I think clear. There is clear attachment, and there's also clear color image. Okay, I think that's what I need. Clear color. There you go. I think this is the one that I need. Now later on we're gonna be using a render pass to basically replace this whole two things, but I'd like to go step by step and show you the whole process. So, but later on we're going to replace these two functions with render pass and frame buffers and all sorts of craziness. But anyway, so we have a pipeline barrier right now and a clear color image. CMD clear color image. All right, amazing. So let's go ahead and see what we could do here. Where is it? Okay, let's see. Now the fact that it gives us this guy a slice, we have to every time, well, we need to anyway, so actually we need to, right? Anyway, so what we gotta do, we gotta go here, I think. And now after we acquire the image, I guess, yes, after we acquire the image, let's see, presents image index. So here we gotta get the image first of all that we're talking about. which we can get from the swap chain. So swap chain dot images, or maybe we need an image view though, not sure. We'll see. So basically we need that guy, image index. There you go. And since we got an image now, we're gonna go through every command buffer, but right now I don't need that. I'm just gonna go pick the first one anyways for now. And yeah, const command buffer is equal to that guy. Okay, good. Now we got the command buffer. What's next? We got a handle there. Cool. So first of all, we got to begin the command buffer. Begin the command buffer. Okay. So since I wrapped this kind of handle into an actual struct, now I could basically easily add this, for example. It could probably fail, I guess. Oh, but I do need the device. I cannot, well, yeah, I need to pass in the device because I cannot add it here. Otherwise, it's not going to be the same as a vacate command buffer, I think. Yep, so we got to add in the device here. Okay, well, let's see, device. Device dot adapter dispatch. Okay, dispatch dot begin command buffer, and let's see what that needs. And yeah, so that needs this stuff, which basically means self.handle. Oh well, self const self is equal to this. Let's go. Then here we got command buffer begin info. So const info is equal to command buffer begin. C dot command buffer begin info, I think. So we have S type, of course, C dot structure type. Vacate structure type. Begin. Let's go. That's the S type. Inheritance info, all that craziness. I don't think we need those right now, at least. Let's see the flags real quick. Command buffer. Well, there's none, I think. What else? There's inheritance info. What is inheritance info? What? Command buffer inheritance. Okay, frame buffer. Yeah, we don't need this right now, at least. So we only need that for now. Begin command buffer. And then, well, could this fail though? That's the real question. Could this fail? Vacate result, yep. Yes. Alright, let's go. What I've done. Okay, so return. Let's see, map vacate error. And there you go. That's how you begin a command buffer. Next up is to end the command buffer. Probably need a device, yes. And this could also fail. Now we need to do something similar to this, I think. here. I guess it's a command buffer end info or something like that. Submit? No. I don't know. We'll see, I guess. Right, end command buffer. Let's see about that. Ooh. Where? Okay, it just takes the handle and it returns the result. Okay. And there you go. So we don't need an info here, but it could error. That's the end function. Next up is, let's see. Now I think let's start with clear. Well, first of all, let's see what's going on here. So after we get our command buffer, basically, we could just say command buffer.begin, give it the device, and then command buffer.end, give it the device. And there you go. Okay, well, and of course the furthest guy, and I gotta wrap it in its own scope. And there you go. Now inside this scope, we could just simply submit command, well, not submit, but record command buffers. Cool. Great. Okay, let's see. And before that, honestly, let's just submit those commands first of all. Just a empty command buffer for now. Let's try to do that. So how to do it? I think c.vk q submit. Yes. pfn vkq submit. Now let's go to const device is equal to a struct. Let's go. All right, q submit. Let's go child. There you go. Equal undefined. And the q submit. Let's see what this takes. It takes a fence. Or it can take a fence. The fence is probably optional. And then the submit info, the queue, and there is this guy. Interesting. And there's a submit info. Here you could actually tell it the semaphores, the command buffers, and the signal semaphore count. Command buffers. Okay. Signal semaphores. Device. Okay. I think I knew what I wanted before about the command buffers. Hold on. So what I was talking about AOS, array of, actually SOA, which is structure for arrays, which is that if we really want to not have to, for example, every time give the device, what we could do, we could indeed go ahead, I think, and basically have a device. Oh, but no. How? Well, in that case, you cannot do this. You have to do some housekeeping or whatever it is here. So, but basically, the idea was that you could say device, vk device, Right, and then you could use this device here. You don't have to pass it, and then basically you could say, I guess, array list, cd dot multi array list, and then you could say command buffer, and you know, stuff like that. And then you would have like command buffers here. Okay, and then you would basically say command buffers dot field or items or what? I think, yeah, items. And then you would say here handle. And then you could just pass this to queue submit, and you can pass it to other stuff. But it does require some other work that honestly I don't feel like doing for just the convenience, basically. So yeah, there's no need. So just remove this guy. Okay, well, what we had, oh yeah, we added queuePresent. So now let's go to const device and let's add that function. Fn, well, it should be called queuePresent, right? Oh, submit, queue submit. Alright, queue submit, and then we could say void or what? Yeah, either an error or void. And then here queue submit, let's see. Okay, let's use self, and then here let's say self dot, well, return map vk error, and then say self dot dispatch dot let's see, queue submit. There you go. All right, queue submit. So what this needs again, it probably needs the device handle, and then it probably needs the submission info. Oh, it needs vk queue first. Interesting. So not the device, the queue. Then this U32, which is weird. So let's have a look. Submit count. Oh yeah. So you could basically submit multiple things there. Interesting. Alright. Well. Let's go. Now here for now, I guess let's just go with one. Call my info. And what else we need? So const info is equal to, oh, you need the fence. Okay, so also probably an optional fence. So fence, oh yeah, well, c.vk fence. There you go. Okay, cool. Now that info is equal to cd, well, c.q submit info. Probably submit info. There you go. And then here we need some crazy stuff. Okay. First of all, of course, is type as always. So vk structure type. And then what else? Yeah, queue submit info. There you go. Submit info. Next up is we got the, oh, by the way, passing the fence here. Oh, well, either at fence or else, oh, in fact, we could just pass in the fence directly anyways, in this case for now. Okay, so other than S type, we have command buffer count. So we can basically get in command buffers. Okay. So for command buffers, I think we can basically do this, then this. Oh, what I'm doing, command buffer, I think. What's the problem with that? Okay, there you go. So we're getting the command buffer now. Now p command buffers is equal to ptr cast. Let's see. Command buffers, let's go. .ptr. Then command buffer count is equal to well, to command buffers.len. Then what's else? Signal semaphores. And p-weight dst stage mask, p-weight semaphores. Oh well, there's a lot of stuff there. For now though, we need the fence and the semaphores, I think. Fence and the semaphores. So signal, so it could wait for semaphores and also signal semaphores. Now we do need to signal semaphores, so it basically should wait for the acquiring the image, and then it should signal the presentation. So basically it would wait for the image to be ready. Then, I mean, in this case it, well, yeah, in this case it doesn't really need to yet, but later on I'd like to do that. So p signal semaphores, but right now let's just go with this S type semaphore. I don't need semaphores, but it, well, let's see. Okay, let's just leave it like this in this case for now. Okay, let's see, cd mim init. Later on we're gonna add some other stuff. c.vk submit info. Is this like a game engine technology? Yeah, we're implementing the rendering. This is graphics programming. Low-level graphics programming, so ptr cast. And welcome to the live stream, John Peters. Welcome. I think that should go ahead. Alright, let's see, qsubmit. Let's go ahead and use this qsubmit function now, I think. Well, let's see. Alright, so try, yes, try command buffers, no, device dot submit, qsubmit. Here we could give it a fence, and otherwise we could give it, okay, interesting, fence. Yeah, I see what's happening here. Is it a bad idea to port a game engine to a browser using WASM or something? It's not really a bad idea, but you can do it, and are you ready to do the work necessary to do it? And also, it depends on the technology you're using. Like, is it capable of doing that? Like, for example, you're using GFW, let's say, for window management, then I don't think you can use it for web. Let's say you'd probably have to use SDL maybe, for example, although I'm not even sure about SDL if it supports web. But yeah, it's not really a bad idea. It's a good idea, but can you do it? That's the problem. So yeah, for example, Vulkan, it won't work on web, at least for now. So yeah, queue submit fence command buffers. Now there's a lot of ways that we could do this. Can put SDL2 on the web, I believe. Shame about Vulkan. Nah, Vulkan is not really made for web, pretty much, because it's very low level and it gives you a lot of control. And the thing is, you cannot afford to give such level of control inside of a web page. I mean, if you're just surfing the web, you don't want a web page to crash your GPU, for example. Or do you? That's the thing. But there is web GPU. Right now, the web GPU spec that you could use. Like, you could use WGPU implementation, or you could use, I think, yeah, pretty much WGPU is the only one that I know of. And also you could use hold on, let's see, OpenGL, I think? No, there is another version of OpenGL which is called, well, I don't remember the name, but anyways. So there's fence here. Okay. Queue submit. Alright, interesting. So here's what I'm going to do. I'm going to remove the fence from here. I don't need a fence anymore here, but in fact I'm going to use it here right now. So get 0. But then we'd have to make sure that this guy waits for the acquire next image. That's the thing. So yeah, and in fact peer present for some reason takes in fences. Really interesting. Ooh. Oh yeah, it actually waits on those fences. It doesn't signal them. Alright, makes sense. Okay. Kinda got confused at some point. Anyways, so command buffers. Command buffers. We already have command buffers, right? Let's go. So right now we need to expose also the semaphores. So let's go ahead and do that. Semaphores. For now, honestly, let's see. What we have in terms of semaphores though. Okay, gotcha. Okay, gotcha. So queue submit, queue present. I have to change some things honestly, but anyways. So let's go to queue submit. Alright. So here what we gotta do, let's see. We need p-weight semaphores, pretty much. And we also need, well, hold on. So it needs to wait on the semaphore. And then it needs to signal a fence. Okay, so we need these guys. Well, in fact, these guys, right? So let's actually get those. and we basically need to wait for those. So here I'm gonna say wait semaphores, and honestly I'm just gonna take in a slice of c.vacate semaphore. There you go. And then basically I'm going to say here wait semaphores is equal to wait semaphore count is equal to wait semaphores dot len, and then p wait semaphores is gotta equal to wait semaphores dot ptr, and let's go. And now what we could do, go back to qsubmit where we're using it. Oops, there you go. And now here I gotta actually add let's see, the semaphores that I have. Handles items. Okay, nice. Nice. So what's happening here basically is that here we're acquiring next image, and we no longer use a fence here, we're only using the semaphore. Now this guy, when it acquired when an image is ready, it would signal the semaphore that we have gave it, which is in this case the semaphore 0, the first semaphore. And then afterwards here we're gonna come to here in qsubmit, and we're going to wait for that semaphore to be signaled by acquire next image. So basically here qsubmit wouldn't run those command buffers until acquire next image, until an image is ready by acquire next image. And then afterwards it would qsubmit, after it's done, it would fire up this fence, and then I'm basically going to wait for that fence. What the heck is a semaphore, and what will I be able to do without it? All right, hold on. And by the way, welcome the Frisco. Okay. So semaphore and fences are synchronization objects. Now the thing is, when you call a function like acquire next image or qsubmit, it will return immediately. Well, there is an exception in acquire next image, but generally, it will return immediately. It wouldn't wait for the command buffer to execute. It wouldn't wait for the it would wait for the submission, I think. But basically, those command buffers would just go to the GPU and then it will return. It would just submit them and return, but it won't wait for them to finish executing. Now, if I want to wait for them to finish executing, I have to use semaphores or fences, etc. In this case, what I'm doing here is I'm using the semaphores to synchronize acquire next image and qsubmit. I'm using the semaphore to make to basically say that I only want to start executing those command buffers that I submitted only when acquire next image have got an image ready. And then you can actually execute. And here I'm using a fence. Now the difference between a fence and a semaphore is the fact that you cannot, hold on. Semaphores are there to synchronize GPU to GPU operations, but fences can synchronize the GPU or the device with the host, and the host in this case is our CPU basically. So you can think about like our code. So here what we're doing basically is we're using a semaphore to synchronize these two GPU operations, which is acquire next image and qsubmit, and then we're using the fence here so we can actually synchronize our code, our program with the submission. With the commands. So basically what happens here is that when those command buffers finish executing, it will signal the fence. And so here, notice here that I'm actually waiting on that fence to execute, on that fence to be signaled, because when it gets signaled, it will get signaled by qsubmit it will, that means basically that the command buffers have finished executing. And that's pretty much it. And here notice that I'm also synchronizing qsubmit with present. I'm passing here the semaphores. So what happens here is that I only present the image when I have finished when I finished executing the commands that I want. Now in this case it doesn't really matter, since I'm not really using the images in my command buffer, so this doesn't really matter in this case. But later on I'm going to add some commands to the GPU that would actually work on that image that we acquired. So basically, in layman terms, we don't want to present the image before we have finished rendering to it, okay? And we don't want to start rendering the images or the image before we actually got an image in the first place. That's the thing. Like, by default, there is no synchronization. You have to use those fences and those, like, you have to use semaphores to basically synchronize the GPU operations between them. And then you also have to use fences to synchronize the GPU with your CPU, which is your program in this case. And also there's pipeline barriers, which are also GPU to GPU operations. In fact, it's, well, there you could use barriers, memory barriers, I think they're called, or pipeline barriers, right? Pipeline barriers to actually synchronize operations that are in the same, that are being submitted to the same queue, basically between the command buffer commands. Now when I'm actually going to start recording commands to the command buffer, they can actually execute in arbitrary order. Well, in fact, not, but anyway, I'm just simplifying this. They could basically execute in whatever order, but if I use memory barriers and some other crazy stuff, then I could actually synchronize those operations and make sure it's actually working in the right time. There's also memory. You also have to synchronize memory. It's not like OpenGL, which you just like all that stuff is being done for you by the drivers in OpenGL, for example, or WGPU, etc. But in here in Vulkan, you gotta do all the synchronization yourself, all the memory stuff yourself. It's like you have full control, basically. That's basically it, hopefully. Hopefully that answers the question. It's kind of a hard topic though, but yeah. Okay, so queue submit, present. Let's see. I see, so we can solve synchronization problems like race conditions. So when a thread wants to use a resource, it checks the semaphore. Yeah, exactly. Like the whole thing is multi-threaded in some sense, because you have the GPU running in its own world, and you have the CPU running in its own world, and then even inside the GPU, you have multiple queues, which also are running in their own world. So it's kind of like just, there's no kind of sense of order. You can only establish order using semaphores and using what is it called, semaphores, fences, and also memory barriers, etc., etc. Actually also what is it called, pipeline barriers, whatever. So yeah, pretty much you got it. So it's all multi-threaded, so you have to use explicit synchronization. But yeah, not sure what I've done until now. Kind of lost it there. Let's see. Command buffer declared here. Missing struct field. Oh, okay. So I could just say std dot well, std what? Std mem 0 in it. Let's go. Okay. And then what else? Okay, we need also this guy here. Let's see, what's the problem here? Oh, there you go. And that's pretty much it, I think. Begin and okay, terminal. Now consider using try and end. It can fail too, so that's interesting. Well, I think I'm going to just remove the defer anyway for now, honestly. So yeah, and here I could basically record the commands. Consider using try. Okay. Alright, PTR cast, yeah. As, let's see, command buffers. PTR as what? Okay, as this. And let's see. Expected type U32 found U size. Bruh. Oh well, let's see, count where I haven't. Oh yeah, well here. So let's actually make that as U32 int cast. Let's go, and then you give it the weight semaphores length thing there. I probably need to edit that too in some other place. There you go. Okay. All right. What is the other stuff? Count. Oh, here too. Something similar to that. Let's remove this. Ooh, well, let's remove this and let's put it here. What else? So expected type found what? Oh, here Q. Nice. So pretty much right now we're just sending empty command buffers to the GPU. Right now we should start actually sending something, and it seems to be crashed for some reason. Oh well, everything has stopped. There you go. Oh well, let's see. Images passed to present. P weight semaphores. Member of present info must be semaphores that are signaled. That have no way to be signaled. What? Okay, let's go back and see the whole thing. Validation error. If weight semaphore count is not 0, must be a valid pointer. Ooh. P weight DST stage mask. Okay. And then what's going on here? That has no way to be signaled. Interesting. Okay, let's see. Alright, P weight semaphores. Alright, so it's telling me that those semaphores doesn't have any way to actually be fired. Interesting. Let's see where I'm using that again. So here I'm passing semaphores. And here I'm actually giving the semaphore. Oh, does this actually signal the semaphore, or it probably does? Not sure what it's talking about, but let's go back, fix one problem now, which is B-weight DST stage mask. So I guess I gotta actually add this to the mix. Is equal to, well, what it is though. B-weight DST stage mask. It's a vacate pipeline stage flags. Oh well, okay. See the vacate pipeline stage. Don't have any pipelines yet though. Bottom of pipeline. Top, is there top? It doesn't matter. I think what I've done, what I pass here, since I don't have pipelines in my case. And we had a segmentation fault. Amazing. Amazing. That's what we needed. Terminate application. Let's see. Let's see. What if we, but why it's a P? P weight, what? Oh, it needs to be an address. Oh well, of course I cannot do, well, let's actually get that flag there. Const flag is equal to this guy, and that should work. Expected type const u32. Okay, well, I guess we could just say int cast in this case. Alright, so 9 u32, and let's go. And with that, there you go. Attempt to implicitly reset command buffer create. Okay, I gotta add this command buffer bit flag. What else? Okay, so let's actually go to where we're creating the command buffer. Sorry, command pool, I think. Yes, command pool. Okay, well, dot flags, I guess, and we have to pass in that guy. Oops. Oh, this is still on. What? Error encountered initializer for flags. But it is not a field of command buffer allocate info. Not a field of encountered initializer for flags, but it is not a field. Oh, okay, makes sense. Buffer allocate info. Okay, let's see the fields that are there. Oh, they're not, it's not here. Interesting. Oh, I think it's probably where we're creating the actual command pool. So let's go ahead and do this. Here. Flags equal to this guy. C dot duplicate field. Oh. Okay, we have fixed that one. Now it's just a matter of solving this error using one command. that I know of, which is the memory, because we're basically going to transition manually the image to a present layout if you want to do it this way. Okay, let's see how we can do this. Well, try command buffer dot. Okay, I gotta add a new command now. So fn, well, we gotta see what we're gonna call it, but yeah. Oh, this can't error, because, well, when you're actually recording the errors, the commands, it wouldn't give you any error at all. But when you say end, then it would actually give you if there's any errors. It would tell you if there's any errors, basically, for performance reasons, I think. So anyways, let's see. So we need self. I don't remember the name of the function, but we'll see. So self, and then there is device. Yes, device. So device, and now I have to say self dot. Actually, not self, device dot dispatch dot, and here we have some cool stuff. CMD pipeline barrier. That's what we need, I believe. And let's see, because this would help us transition the image layout of the swap chain image. Now this would be done for you by a render pipeline, by a render pass automatically, as we're going to see in the future when we actually do that. But right now I'm just trying to basically show you how to clear the window image with the color without using the render pass or shaders or pipeline or none of that. Just manually using commands, GPU commands, and I think that's would be interesting. So let's see, pipeline barriers. Well, VK CMD pipeline barrier. Because, yeah, well, all right, there's a lot of crazy stuff here now. But is there a layout? The old layout and members of any included in this command must be equal. Oh, I think it's an image memory barrier, maybe. Hold on, Vulkan image memory barrier. It's, let's see. Global memory barriers. Yeah, probably image memory barrier. Yeah, that's what I need, not this one, because I don't even have a pipeline in this case. So question about image. Yeah, it's an image memory barrier, but I gotta find the function though. Let's see. Why there's no registry about that? What? Oh, yeah. VK memory barrier. Oh well. Maybe VK image memory barrier? Don't remember. There you go. It's defined as. Alright, so you give it the access mask, the destination, and there you go, old layout and new layout. This is what's interesting. And source and destination key family index image. There you go, sub-resource range. Nice. To access to memory through the specified image sub-resource range. Oh yeah, I think you used it here. Hold on, pipeline. There you go, vacate image memory barrier. So you basically, first of all, I have to actually make this guy, this image barrier, memory barrier thing, and then I gotta pass it to as a command to this guy. But how does it know which one it should use? Because basically I think this is kind of like a union. Oh, you said the count to 1 here. Okay, makes sense. Makes sense. Alright. Makes sense. Alright, I don't know if there's still enough time. Let's see. Not sure. I guess let's just try, I guess. Okay. So pipeline barrier, okay. Now here, pipeline barrier. Or honestly, instead of saying pipeline barrier, let's just create a transition, okay? Transition image, and then it basically takes in a device. And let's see, device. Do we really need device? Yes, to get the key family. Then we can get the image from the swap chain, and then we just need the new layout and the old layout. For the first time it would be indefined for old layout, but okay. So let's actually, we need the old layout, which is gonna be c.vk old. Oh, image layout, okay. And then you also need the new layout, transition image layout. And while we're not going to be using all this stuff later on when we have a render pass, but this would be useful later on for, first of all, to understand Vulkan basics without the noise of Vulkan Vulkan pipelines. That's the first thing. And second thing, because it may be useful later on when we're dealing with textures and the MSAA, the multi-sampling of the window. But so yeah, pretty much amazing. So c.vk image layout, let's go. I still don't understand perfectly all the synchronization stuff. It's kind of weird, but yeah. Okay, so how to deal with this? So it needs a command buffer. And all this craziness. Okay. So first of all, this is easy. Handle VK pipeline stage flags. I don't have any flags for pipelines, but I guess 0 for now at least. I don't know. C.vk pipeline stage flags. I mean, I don't have a pipeline, that's the thing. So 0, I guess. And dependency flags, I don't know what's that yet. I don't need it, I guess. Validation would tell me otherwise, maybe. What else? There's a U32 though. Well, I gotta look up the documentation to this guy. Well, VK CMD pipeline barrier. Okay, it's a stage mask. Alright, and then dependency flags. Okay, let me actually see the valid usage. What does this stuff have to do with the thing? Well, anyway, let me just try to figure it out anyways. So, well, what we need now. Let's go back. Pipeline, well, transition image, there you go. So here we need a memory barrier. I don't care about that one, so I'm gonna say 0, which means I don't need memory barriers right now. And yeah, 0 for vacate buffer memory barriers. But yes, I need one image layout barrier right now. So as you can see, this is kind of like designed for batching, and so I'd like to design my program to actually go with that, but right now I just trying to make things work. So yeah, the more general the thing, the harder it becomes to design and make it work. So anyways, image barrier. All right, so image memory barrier. Const barrier. Now here c.vacate image memory barrier. And let's see. Now the old layout, we got that out of the way. The new layout, same thing. And now we gotta figure out the rest. Image, we got that too. And we need that actually. So image vacate.image. Oops. There you go. Okay. Now we got these. Now we just gotta figure out the other stuff. The source key family index and the destination, those won't change. So I'm just gonna say self.device. Oh, device.to family. Add actually adapter.key family index. Let's go. Same thing with DST key family index. We're not gonna transition that. Key family index. There you go. What else? There's src access mask and sub-resource range. Okay. Sub-resource range is interesting. I think we need that. So c.vacate sub-resource, yeah, sub-resource range. Oopsies. And here we got the aspect mask. Well, if I really want this to be general, I also have to pass this, honestly. Yes. We can get this from the swap chain, but we're not storing this though. So, okay, cool. So I think let's just say sub-resource range. So this could be used with other images other than our use case right now. So yeah. We're just trying to transition the image. So image sub-resource. Oh well, sub-resource range. Oops. c.vacate sub-resource image sub-resource range. And let's go. That's pretty much it. I think we got this out of the way now. Now we just gotta use this guy. Hopefully. There is the other stuff that I actually ignored. The other fields that I ignored, which I'm not sure yet what I'm gonna do with them. Like is it just fine to pass in 0? But basically the validation would tell me. So yeah, std.meta, no, mm.child, no, mm 0 init, right? Oopsies, 0 init. Now we got that. Well, in fact, we gotta pass in this guy, add a point there, and do this, and then finally do this. There you go. So this should be enough for transitioning the image layout, hopefully. Okay, let's see. And in fact, I did create the sub-resource range before for the swap chain, so maybe I could snatch that. There you go. This is it. Let's just take this out, and let's go back now to the drawing board to actually begin. There you go. So now between begin and end, we gotta say command buffer dot transition image layout. And by the way, it's important to, like, if you don't want memory leaks, or basically leaks, to not do some code that could fail here. So yeah, because we're not guarding on that yet, at least. So anyways, so device, right? Here the image is basically the image. There you go. Sub-resource range, I snatched that. There you go. The old layout is too simply indefined because the image, well, indefined. So c.vk image layout, oh well, vk image layout, there you go, indefined. And then the new layout that we'd like is present src khr, and let's go. So I'm transitioning it to this layout so I can basically silence this error right here that we have here that says that to be able to present the image, you need to transition it to this guy, to this layout. Too simply. So yeah, pretty much. VK image layout and defined. Now, I could maybe make a function called like transition color image layout, honestly, and then I could too simply go ahead and, but anyways, who cares? So that's pretty much it. Just gonna make sure to do this, and there you go. I think that should be good to go, isn't it? Isn't it? Let's see what's gonna happen there. Let's see. Oh well. So let's see. Okay, it crashed on me, of course. Come on. Okay. Alright, let's see what's happened there. Oh, I forgot the S types. Interesting. Do I need an S type here? I don't think. Yeah, I don't think. Sub-resource range. No need for S type there, but we need an S type in, I think here. The S type is equal to c.vk structure type image memory barrier. There you go. That's the type there. What's the other one? So, okay. CMD line barriers, SRC stage mask must not be 0 unless synchronization 2 is enabled. Interesting. And what else? All elements, anyways. Memory barriers. Okay, SRC stage mask and DSC stage mask. Alright, interesting. So let's go ahead and try to fill in that SRC stage mask and stuff like that. Okay, well, where's the image memory barrier thing? Transition, there you go. And let's find out. So SRC, stage mask, okay. Let's find out what that could be. Let's see, image memory barrier. I think I have it here, right? So SRC, VK access. Oh, I see. Makes sense. Now I remember this guy. So it would be access none. Yeah. I mean, if we had, well, anyways, right now we just need to use VK access none in SRC access. So vk access none, and then DST stage mask. Let's find out what we could give this guy. Alright, vk. So what the presentation would do, it would read from it, right? Let's see. Oh, provided by vk Vulkan version 1.3. What? Really? Interesting. What? So I guess I cannot use it since I'm using 1.0 or I guess 1.1. Alright, so I can only use these guys. Interestingly. Okay, let's find out. Host write, host read, memory read, transfer read. Oh, okay. Alright, well, a presentation would probably transfer the image, I guess. So, and it would read from it, I think. I would guess. I would guess this guy. Transfer read. I would guess. The other thing now. Input attachment, that's for shaders. Uniform vertex attribute. Now, how can I go with access none? Interesting. I would guess, well, I guess vk access host right. I'm just gonna try that out. Let's find out what's gonna happen there. Alright, well, what's going on? Stage math, but it's not a field of. Ooh. Did I place it in the wrong section? Image memory barrier. Let's see. vk image memory barrier. What it is. There you go. So what is it called? Oh, it's src access mask. Is there like a oh, well, in fact, hold on. Well, it was talking about the stage mask, not the access masks. Interestingly. Command buffer. vk cmd pipeline barrier. Pipeline barrier, src stage mask. So no, it wasn't really yelling about this stage mask. Oh. Well, that's the access, no? Okay, I think I got it. So, in fact, that thing is inside of vk cmd pipeline. There you go. So it should be here. src stage mask. There you go. So vk pipeline stage flags. Let's have a look. Right. Is a bit mask type for sender mask type. Okay. There you go. Alright, interesting. So maybe I don't really need to give it src like these guys access masks. So I'm just gonna comment them out for now. Let's actually go back to cmd pipeline barrier. And okay, there you go. What? Hold on, what the? Oh, here, right? Let's see. Well, I think well, interesting. Okay, so it's inside of, yeah, the first two parameters. Interesting. Okay, so what we're gonna do? Well, it's, I think, top of pipe bit. We cannot say stage none for some reason, interestingly. Okay, so top of pipe, I think I would use that. So, well, where is it? Here. That's the first thing. The other thing would be the destination. Let's see. Where is that guy? Okay. Alright. All commands, all graphics bits. Transfer. It's probably transfer. When it comes to presentation, it's probably transfer. So, but we'll see. All right, so there you go. I think, let's see now what's gonna happen. It's probably gonna crash again, but let's find out the actual warnings or errors or whichever. Okay. Ooh, did it actually work? Yeah. Oh my god. Cannot believe this. Interesting. So, right, at least right now we do not have those stupid things anymore. And those stupid warnings. Now, I just gotta figure out what the is going on with this one. So, VKQ present. P waits semaphores, Q, VKQ is waiting on semaphore. A that has no way to be signaled. Must be semaphores that are signaled or have semaphore signal operations previously submitted. Well, didn't I actually give the semaphores to this guy? Hold on, let me actually have a look into acquire next image. Oh, there you go. What it takes. It takes a semaphore, but what it does with that semaphore? To signal. So what the, why? To signal. To signal. Well, we're actually getting the semaphore here. And fence. No. So this should actually signal it. So what's the problem here? I don't get it. Let's see Q submit again. So just too simply passing in wait semaphore count is wait semaphores dot length. Honestly, just to keep this very, very simple, you know, I'm just gonna say this one semaphore, okay? And you know, just one, and then here you just give it the address of that guy. Too simply. The address of wait semaphore. And one here. Oh. Q submit. Well, it does have to wait, right? Okay. And let's now recheck what happens here. That would also be interesting. So yeah, it is passing semaphore here. So that should work. Weird. Okay, well, let's just to make sure. Here is the same semaphore. Same semaphore we're gonna use in both places, here and here. This should signal it and this should wait for it. Pretty simple. I don't get this. What now? Like, bro, what is waiting on semaphore? Really? Acquire next image. Q submit. Ridiculous. Acquire next image. Cannot believe my eyes. semaphore. Well, here's a quick thing that we could use to check to make sure that we're doing it right. API dump, and I'll see exactly what address of semaphores it's passing on. So if there's any funny kind of business going on there, I could see it. Okay, let's see. So queue submit. It's waiting on this semaphore, this address. All right, amazing. Okay, now tell me which semaphore the other guy is signaling. Let's see, begin there you go. What semaphore? Okay, 0xf27 f70. What? It's the same exact semaphores. What the oh my. Okay, let's go back to validation. I cannot believe my eyes. Is that like a bug in the validation layers or something? Like, and why it's giving me this address, this weird address? What? See. Oh well, anyways, so I think that's it for today's live stream. I gotta go for now. Alright, and so we're going to continue this probably tomorrow, inshallah. And so yeah, is there any questions before I end the live stream? Let me know, or otherwise just say goodbye. If there's any questions, let me know. By the way, what we have done so far. Okay, recent events. Yeah, we're getting there. I just have to fix that stupid problem, and we should be good to go. Alright, let me know if there's any question before we end. Add wait, reset. I should redesign the way I'm doing the fences and the semaphores. Okay, transition, fences. Yep, we didn't do a lot, but yeah, we had a lot of decisions to make, that's why. So yeah, that was it for this live stream, and see you later everyone. Goodbye.